SWOT is a mission that is specifically designed in part to observe rivers, and it's also being designed jointly by NASA and the French Space Agency. I was born in France, but I've lived in the US for 18 years now, and I study rivers. So SWOT is a little bit of a match made in heaven for me. The kind of science that I'm interested in is trying to understand how much water flows down the rivers of the world, and SWOT will be able to make one such measurement for all of the largest rivers of the world. So we'll be able to get a global, unified picture of surface waters from space. This in itself will be a scientific revolution. I think that's going to have a big impact on water management. I like to say that water is my friend. Water is my happy place. I was born with a physical disability that affected both of my legs. Being able to walk now was not a done deal at birth, and it still involves a significant amount of discomfort and is a constant reminder of having been born different. For as long as I can remember, water has been the only place where I felt comfortable, where I felt normal, where I felt like I could do things like everybody else. When I get in the water, it's just like, you're floating. When you're floating, it's just like all the pain goes away. As a kid, my parents would take my brother and I all the time to jump in the Mediterranean. But to this day, we still do it on New Year's Day every year. Planning for future generations requires us understanding how much water we have. And SWOT will be able to provide that global view of the world's freshwaters. And in my opinion, it might very well become the key that unlocks surface water observations around the world and unleashes surface water management. So it might help us make sure that everybody gets access to fresh water. Now more than ever, it's important to recognize that water connects us all, and it might be the one thing that unites us all.
I love being out in the field. Coming out to the field keeps me in touch with reality. I'm Marc Simard. I'm a SWOT principal investigator, and I study the dance between the tides and the rivers. I'm from Quebec, Canada, from a city called Jonquière. I started studying physics with specialization in astrophysics and became enamored with the environment. And I actually became president of the environmental club. I did a switch and I started to apply what I learned in physics to the environment. So here's a water level gauge. Water level gauges, are sparse points here and there. SWOT, on the other hand, will give us these same types of measurement on the ocean, the lakes and rivers of the entire globe. The Mississippi River Delta currently is losing land at a rhythm of about 1 football field every hour. There are about 350 million people living on deltas around the world. They live from the fisheries, the agriculture, the aquaculture from those deltas. So if we lose those deltas, we're not only talking about losing land, we're also talking about losing livelihood for millions of people. SWOT data will give us a global perspective of how these deltas can survive and keep up with sea level rise and other impacts of climate change. Looking at the deltas around the world, it's an extremely dynamic area. It's like the river is dancing with the ocean. This work is meaningful to me. It has a direct impact on those millions of people that live from the resources of these deltas. So I think finally I found a meaning to all of my research.
Coming to work every day, it's always really nice to know that the system that we're building will collect science data that will be spread publicly, that the data will help people. Hi, my name is Christine Jabara, and I'm an integration test engineer at JPL. SWOT is an Earth-orbiting satellite. It stands for Surface Water Ocean Topography, and it'll give us more accurate data on how the water levels, the freshwater and the saltwater levels, are changing with time. The day-to-day varies a lot. We're usually either setting up for a test, testing, breaking down from a test, or moving the spacecraft. The coolest parts of SWAT to me are the engineering bits that are slightly extreme. So I've really enjoyed working on the deployable antennas. It's nerve-wracking, but it's a well-rehearsed dance. And when the antennas actually deploy, they're really beautiful. They're moving slowly and intentionally, like a butterfly. I grew up in Houston, Texas. I was very lucky to be part of the Girl Scout sailing program, where they taught us not only how to sail, but they taught us the very basics of aerodynamics and how the sailboat worked. I became an aerospace engineer because of that program. The ability to say, oh, I know how this works, and then going to implement it in a way that was fun and exciting was really rewarding. If I were to tell a little girl how to get into engineering, I would tell her just to get started in whatever way feels exciting and natural. It gets a lot easier once you just get started and start tinkering with things and building whatever excites you. It's not lost on me at all that I grew up sailing and I still love the water, and the spacecraft that we're building will help us track our oceans and our lakes and our rivers. Hopefully we'll be able to sail for much, much longer in beautiful blue waters.
When you turn the faucet, we take it automatically that the water will come. There's places in the world don't have these opportunities. My name is Tahani Amer, and I work at NASA as a program executive, and I'm excited to be part of the SWAT team because water unites us all. SWAT is one of my missions, and my function is to ensure SWAT mission success. Working with NASA taught me one thing, is to be a team player and to work with hundreds, sometimes thousands of people. And you really need to appreciate everybody in the team and be able to work together. So collaborations and relationship build bridges, and SWAT will be that bridge across the world. SWAT is a very unique project. We need to understand the water cycle in a lot of detail. And SWAT is going to be one of the first satellites that will measure global water. So we'll have a better understanding of our water and our water accessibility. We have to be able to understand the changes of the water around us, and then we can conserve water. My father used to work in water too. He used to work for the Nile River, for the High Dam in Egypt. Growing up in Egypt, my dad was always encouraging me. He said, boys and girls, there is no difference between them. And my dad was the one who was really supporting me to do science. My faith gave me the confidence and the strength to do more so I can show the whole world that Muslim woman can do anything she wants to. One of my passions right now is making sure that everybody has a voice in the table and to have a pipeline with the new, fresh ideas from young engineers and scientists. And what I love about SWAT is water is the birth of everything. And it's very rewarding to me that I can do even a baby steps to save our planet.
Right before auroras dance in the sky, there's often an appearance of a mysterious shape. It drapes across the sky like a glowing pearl necklace. Scientists call them auroral beads. Structures like these can reveal how Earth's magnetic field interacts with solar material gushing through space. Understanding these interactions better could help scientists protect low Earth orbiting satellites from extreme solar events. But until now, how the beads form has been a mystery. With the help of NASA satellites and computer models, scientists have the first evidence of how auroral beads form. All auroras are created when charged particles from the sun are first trapped in Earth's magnetic environment and are then funneled into the atmosphere. But scientists are now realizing that small changes in the magnetic environment can cause big differences in how the aurora can look. To analyze the auroral beads in more detail, scientists took observations from NASA's Themis mission. 3 of the Themis spacecraft study near-Earth phenomena that triggers auroras. Scientists then combined THEMIS observations with ground measurements and powerful computer models. This is the result. It's a simulation of the near-Earth environment that scientists can analyze on scales from tens of miles to 1.2 million miles. They found that when particularly large streaming clouds of plasma from the sun reached Earth's magnetic field, they created buoyant bubbles of plasma behind the planet. Just like a lava lamp, the buoyancy between the bubbles and heavier plasma creates fingers of plasma about 2,500 miles wide that stretch down towards Earth, creating the distinct pearl necklace structure in auroral beads. From the ground, the beads average about 30 miles wide. Scientists hope these models will also be able to explain other small-scale structures seen in the auroras. The new results show us that even small, short-lived events within auroras can be linked to big global phenomena in our near-Earth environment.
SWOT is the Surface Water and Ocean Topography Satellite. It's an international satellite that's going to give us this complete view of the surface water here on Earth, what's happening in the lakes, reservoirs, rivers, and also in the ocean. It'll tell us about how sea level is rising along coastlines and in the open ocean, and really give us a good understanding of how surface water is moving about the Earth.
Our goal is to provide data, forecasts, watches, and warnings at some key locations like the Willamette River in Portland, which is a major U.S. city that historically has seen some catastrophic floods. The better quality of the data that we have that feeds into our models, the better the forecasts are going to be, the more time that people will have to protect themselves and their property and ultimately our communities. A tool like SWOT is going to help us with making these really difficult projections and predictions for the future.
Ours here in the Army Corps of Engineers, the water managers here, they use weather prediction, they use hydrologic models, and the hope is that data like SWOT might be incorporated into those predictions to help them better understand this water body's filling and we don't want to overtop the dams, might want to start letting water out really quickly. They have to make a lot of complicated decisions. When you get a big storm event, we want to keep the community safe in the best way that we can. So how do we best manage operation of these reservoirs in terms of putting water out downstream to prevent flooding at a larger scale?
In lots of states, there are, hundreds, thousands of reservoirs, and many of those reservoirs don't have automated gauging available. And so these agencies have to kind of estimate how much water is in them and how that's changing. And with SWOT, they can just monitor that directly from space.
For us in Alaska, we have many, many rivers, and only a few of them are measured, or as we say, gauged. If we have data on when flooding is occurring or might occur, we can get crews out there to look at the bridge to make sure that the bridge and the associated roadway are still safe. If we can start collecting data on all rivers above a certain size remotely from satellites, it really opens up the amount of rivers that we can help understand what happens when they flood or how they flood. And that really improves our ability to manage our infrastructure and to design new infrastructure. That is where SWOT will really make a big difference.
One of the partners we're working with is the Department of Defense, and they're trying to fill gaps in the data that they have along the coastlines. Our military is obviously very concerned about what's happening on global scales, and they have installations across the globe. So SWOT will potentially provide an opportunity to fill in some of those gaps, allow them to make the impact assessments that they need for sea level rise in their facilities. So trying to understand and give them the information they need to plan for and then potentially adapt to these changes is really critically important.
Coastal wetlands like the Mississippi River Delta are extremely important because it acts as a buffer between us and the threatening ocean. With SWOT, because of its high spatial resolution, we'll be able to resolve water surface elevation right at the coast. So this is quite important because as sea level rises, the ocean will migrate into the land, bringing more salt into the land. So it threatens the infrastructure, the biodiversity in the wetlands along the coast. Hopefully, the types of models that we're producing can support how they decide to manage the river delta. And SWOT on its own will allow us to upscale these types of studies to the world.
Yeah, I'm really excited about the new information we'll get from SWOT and how we can start to couple it to some of the needs that we see, both at the coastal interface and also on land. I think we can potentially see some immediate impact once SWOT's launched in these communities.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind: the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Mission Specialist.
I'm Jeremy Hansen. I'm a Mission Specialist.
I'm Victor Glover. I'm the pilot.
I'm Reed Wiseman. I'm the commander for the Artemis II mission to the moon.
To the moon.
To the moon.
To the moon.
When I was young, I had a poster of the Earthrise picture, the famous picture that was taken on Apollo 8. And the fact that it was a human behind the lens that made that picture so profound and changed how we all thought of our own home was so amazing to me. The moon is not just a symbol of thinking about our place in the universe. It's not just a symbol of exploration. It's actually a beacon for science. It's a beacon for understanding where we came from.
You know, pushing ourselves to explore is just core to who we are. It's a part of being a human. That's our nature. We go out there and we explore to learn about where we are, why we are, understanding the big questions about our place in the universe. The exploration we're doing is the first few steps on the path of getting humans to Mars.
The Artemis campaign and missions have set such an ambitious goal for humanity that it's inspiring contributions from around the globe. Not just one nation is inspired and moved by this, but nations from around the globe are coming together.
When I look at the Artemis II crew with Victor, Christina, and Jeremy, they want to go do this mission. They are keenly driven. They are humble to a fault. It is so cool to be around them. Artemis II is a huge mission, but I hope we will look back and realize that this was one tiny step in humans on Mars and a sustained presence on our moon.
Force engine start.
Artemis II will be NASA's first crewed flight test of the Space Launch System rocket
and Orion spacecraft around the moon.
To verify today's capabilities for humans to explore deep space
and pave the way for NASA's long-term human and scientific presence
on the lunar surface.
We are ready.
We are going
to the moon
for all humanity.
We are Artemis.
On September 11th, NASA astronaut Frank Rubio completed his 355th day on board the International Space Station, surpassing the record for the longest single spaceflight by a U.S. astronaut, which was previously held by NASA's Mark Vande Hei.
Frank, you've made all kind of records.
Agency leadership congratulated Rubio on the accomplishment during a call to the station. By the time Rubio returns home on September 27th, he will have spent about 371 days in space. The crew of our SpaceX Crew 6 mission is back home after spending about 6 months on the space station. On September 12th, a few crew members, including NASA astronauts Steve Bowen and Woody Hoberg, talked about the mission during a news conference at our Johnson Space Center. The highlights of the flight included Bowen's U.S. record-tying 10th career spacewalk. Our OSIRIS-REx spacecraft recently made a course adjustment to better position itself to release a capsule carrying sample material from asteroid Bennu toward the designated landing zone in the Utah desert. The capsule is scheduled to make a parachute-assisted landing on September 24th. OSIRIS-REx is the first U.S. mission to collect a sample from an asteroid. According to our Goddard Institute of Space Studies, the summer of 2023 was our planet's hottest summer since global records began in 1880. June through August was a combined 0.41 degrees Fahrenheit warmer than any other summer in NASA's record. This new record comes as exceptional heat has swept across much of the world, exacerbating deadly wildfires, resulting in searing heat waves, and likely contributing to severe weather. For more details, visit nasa.gov/Earth. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/Twan.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
It has this direct window to the rest of the universe. There's nothing in between the rest of the universe and Hubble. There's not a single astronomer in the world whose life hasn't been touched by Hubble.
Hubble will be one of the great stories of all time. We will remember it with reverence, with the legacy, with the foundation. It gave us the optimism and the hope to reach for bigger things.
The world's most brilliant astronomers do miracles with this observatory. And it just keeps going on and on and on, and my jaw keeps dropping lower and lower with each new discovery.
Scientists around the world, together with science enthusiasts, the public, science supporters, came together to see here's an opportunity where if we put our wits together and our support together, we could build a platform that opens new eyes to the universe. Let's go for it.
Telescopes from Galileo's simple instrument to modern mountaintop observatories are all hampered by the Earth's turbulent atmosphere. The best place for an observatory is in the heavens. Now the Space Shuttle, created by NASA, America's space agency, has the ability to put one there. The periodic revisit of the shuttle will allow for the replacement of components and routine maintenance. This ability to service the telescope through human care will extend its lifespan up to 20 years.
Telescopes on brief rocket flights have brought us hints of entities we never knew existed.
flights have lifted telescopes 8 miles into the air to take some of the clearest photographs of the sun ever obtained.
Another group of astronomers told a recent meeting of the American Rocket Society in San Diego, California, that they are designing a satellite that will carry a bank of telescopes into an orbit 500 miles or 800 kilometers high. By thus sending a telescope up above the Earth's atmosphere, they hope to pierce a blanketing ocean of air that has, for the most part, obscured man's detailed view of the universe.
Well, astronomers had wanted for generations, actually, to get us a telescope above the atmosphere. The first reference I'm aware of is back in 1925, that it was suggested that we needed a telescope in space. I've read that one of the astronomers at Princeton, this was probably in the 30s or 40s, said that when he died, he wanted to go to heaven and take a telescope with him. And so when the possibility of a telescope in space opened up, astronomers jumped on the idea.
I certainly remember the very first time I went into the enormous clean room where Hubble was being built. I mean, it's 90 feet tall and 120 feet long and hyper clean air. And the telescope just, I mean, it just looked like something Tiffany's had built. We're going to look for the label somewhere that's a telescope by Tiffany's, just glistening silver, fabulous, gorgeous piece of work, huge. So that's one real favorite memory. First sights always leave a deeper impression.
It was mind-boggling. I envisioned Hubble being big. I did not envision Hubble being huge. And Hubble was huge. Since I had already flown a shuttle mission, I knew how big the shuttle was, and I knew how big the shuttle's payload bay was. Hubble was too big. And the first impression was, how the hell are they going to fit that in the payload bay? That is a monstrous payload.
What was happening in the context of science here? We were building an Earth observing system to study our planet, very evocative, ozone holes being measured, studying the sun. We had had a couple of missions to Mars that showed us it's not the way we thought it was. Tough. Soviets had landed probes on Venus for about an hour, pretty hellish. We had the Voyagers going out of the solar system, and that's it. That was our view. A few little points of light flying around, but they were narrow. Hubble was focused on the big picture. And the big picture is always fun. It has something for everyone. Some people call these great missions of exploration, they're kind of like the cathedrals of the 21st century. And in the Renaissance, people built cathedrals. They were multi-generational. They were great architectural renderings that reached to the heavens. Now we go to the heavens and we follow the light.
I remember sitting around the dinner table the night before, and we had talked off and on about what was gonna be the significance of Hubble. Talking about what we thought Hubble's legacy was gonna be and stuff. I mean, things you can't imagine. None of us could definitively say what we thought it was gonna be, but all of us agreed Hubble was going to be something absolutely spectacular that was gonna revolutionize the worlds of astronomy and astrophysics. We just didn't know how. And I think we underestimated the scientific and technological significance of Hubble because it has dwarfed what any of us imagined it would ever do.
Sound suppression water system has started. T-minus 13 seconds. T-minus 10, go for main engine start. We are go for main engine start. T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Discovery Houston, just wanted to let you know that the ground is currently configured for HST main bus activation. So we're ready when you are.
And Houston Discovery, the transfer to internal power is complete. The umbilical is dead-faced, and we'll be standing by for your go for umbilical release.
Roger, Discovery. Discovery, your go for umbilical disconnect.
The Hubble deploy day did not go well. You know, in the end, we successfully deployed Hubble, and Hubble went on to greater things. Deploy day was long and arduous and nothing at all the way it was planned. From the moment Steve Hawley attached the RMS, mechanical arm, things went wrong. Steve was supposed to be able to just pull out on the translational hand controller and have the arm lift Hubble straight out of the payload bay. That's not what happened. I mean, Hubble's 25,000 pounds of mass. Granted, it's weightless in space, but it's still a 25,000 pound mass. And as he began to lift, it began to twist and turn, and we saw it immediately. And so I said, Steve, stop, something's not right. And so that necessitated Steve now going to a downgraded mode, which was moving joint by joint. So for the next couple of hours, Steve Hawley literally had to lift a little bit, readjust a joint, get it straight again, lift a little bit, readjust a joint, or roll it, or do whatever was necessary to keep it as much in its orientation as it was in the bay as possible. But that took hours instead of minutes, the way it was supposed to work.
The thing about Hubble was, we launched it cradle in the payload bay with electrical power umbilicals attached to the back. And once you pulled the plug on that umbilical, Hubble was on its batteries. And there was a fixed period of time, a maximum period of time, that you could run it on its batteries without the solar rays being unfolded to sustain and recharge the batteries. If you got to the end of that time, the batteries would reach a point where they were not recoverable. So that said, I forget now how long it was, something on the order of 4 hours. Well, if anything needs an EVA backup, and we could back up all that stuff, we could crank open the solar rays.
And as the crew just confirmed, we're seeing both blankets beginning to unfurl on the port side solar array.
So far we see good smooth motion both sides.
And so the first solar array, went out both sides. No problem. It took a few minutes. Everything was just like it should be. Second solar array sent the command. It got about, 16 inches and quit.
Houston Discovery, it looks like motion stopped with just about one panel showing.
And we see that too, Lauren. The DCE is off.
And as it turned out, of course, the second solar array did not unfurl correctly. It jammed partway out. And Bruce and I left the flight deck and dove down into the middeck with Charlie Bolden and suited up, and we were all buttoned up. The airlock was sealed. In fact, we had dumped half the air out of the airlock. We were about to get the go for EVA and proceed on outside.
The other thing I need an answer to is if I can go ahead and commit the EVA with the thought of going out and cranking it out. If whatever they're about to do fails, they want us to just press on to back them up. We need to get on with it.
Okay, flight, I'll come back with the answers.
I need answers now.
Flight FAO.
Go ahead.
Yeah, I don't feel comfortable waiting until after
I don't either.
6:20.
That's why I want the answers now.
Yeah, 6:20 is my drop dead time from adding up all the times.
Okay, I'm going to have them press on. All right, Capcom, tell the crew we want them to press on into EVA, and we'll stop them whenever we have to. Just quickly, we got 4 minutes on this pass.
Discovery used.
Discovery, go ahead.
Okay, with the panels that you got out there right now, it's not satisfactory to stay overnight. So we're going to have to move out on the EVA.
I was scared. I had never suited anybody who was going to go out in space. And I knew that if I missed something, if I missed a glove, you know, if I didn't get it fastened right, or something on the helmet, they were going to die. And it was going to be my fault. So even though this guy's come out of combat and all other kinds of stuff, I was scared because I had never done this before. And so I knew my crew members were dependent on me. And we were getting ready to let them open the outer hatch when the ground said, "Hey, stop." And we said, "Okay." They said, "We got an idea."
We think there may be some problem with the tension monitoring software. We've got the DCE back on. We're going to disable the tension monitoring and resend the proc to deploy the minus SDM.
Okay, hit it.
And the irony, this is the day of ironies. Early in the morning when the solar array first stopped, Bruce came up with this crazy, Bruce McCandless said, I don't think there's anything mechanically wrong. I think it's the tension monitoring module. And we all looked at Bruce and went, "The what?" Everybody but Kathy. Kathy had heard of the tension monitoring module. And so Bruce said, it's this software module that we put in to protect the solar array. And in case we got a mechanical jam or something, we didn't want to rip it and destroy the telescope. So we have this software module that would stop it until we could diagnose the problem and then correct it and then let it go out. This young man down here at Goddard, and I say young man because as I understand it, he was a very young flight controller, on console said, "Hey, I don't think we've got a mechanical problem. I really think it's the tension monitoring module. And if you give me permission, I can no-op the tension monitoring module. I can turn it off. You know, I'll make the 1 a 0, and I think everything will be okay." So between Houston and Goddard, and I think Bristol, England, and everywhere else in the world that had anything to do with Hubble, they mashed on this thing for hours, and they said, "Okay, try to deploy it again," and hit the deploy switch, and solar array went out.
It's fully deployed. The micro switches confirm it.
Okay.
And for Bruce and Kathy, we'd like you to stop the airlock depress at 5, please.
Rendezvous.
We're go.
Fido, go.
Eagle.
Go.
Ecom. Go.
Inco. We're go.
FAO.
Go.
Max.
Go.
PRS.
Go flight.
EVA.
We're go.
Sergeant, you're still go?
Go.
Capcom, we have a go for release.
Discovery, go for Hubble release.
Okay, we have a go for release, and we're going to be a minute late.
Okay, Charlie.
And all Steve had to do was pull a trigger that opened the grapples that held the grapple fixture, and it was breathtaking, and it was beautiful as it got farther and farther away, but it never went out of sight because it was so bright and shiny.
So the irony of all of this is that after 5 years working together on the Hubble telescope, longer than any other person on the crew had worked on the Hubble telescope, the view that Bruce and I had at the time that Hubble was deployed was the blank white wall of the inside of the airlock. Never saw it.
Kathy has never forgiven me. She blames me for leaving her in the airlock. So, I mean, you know, a couple hours later I go down there. They've got a lot of vacuum time, but no space time, no spacewalk time. And so I repressurize the airlock, get them out, put them back on the wall, get them unsuited and everything, and they're just, but we had a lot of images for them.
Engineering things that have never been done sometimes have issues. Designing the preeminent viewpoint of the heavens, the Hubble Space Telescope, was not without, sort of new inventions that were never done before.
The first images from Hubble were frankly a little disappointing. They were not as sharp and crisp as we had hoped. It turns out that the mirrors had a slightly misshapen form.
This special mirror, 2.4 meters of specially ground glass designed to capture the light of the universe back in time, billions of years, had an aberration, the way my eyes have an aberration. and I wear glasses. And so there was an initial, oh my goodness, what can we do? This icon of exploration that took 50 years to think about to fly has a problem.
And I'm positive that if we all had written down the 100 most likely problems with the Hubble Space Telescope, if everybody involved with Hubble had written down those top 100, not one of them would have listed the mirrors the wrong shape.
We feel that we can characterize the problem, the spherical aberration problem, well enough that we can take advantage of an insurance policy that we haven't talked much about, and it hasn't been in the press much, and that is we started a long time ago to plan a maintenance program. That is, every 3 years we plan to go up with the space shuttle, change out instruments, change out things that broke, the gyros or something might break. We have gyros in stock. In fact, we have in stock, in storage, most of the critical components on Space Telescope.
So we promised that we had a way to fix it, and we put a new camera in with corrective optics in it that would cure the optical problem.
Right as we talk now, we are building a second wide field camera. And it's not too late to put a corrective optic. You can almost think of it if you've got bad myopia, which you can say our telescope has now, and you put your glasses on, you can correct totally and get 20/20 vision. That's what we would do in the wide field camera, the second wide field camera. We would change one little mirror, relay mirror in there, take out the aberration that the primary mirror causes. That is, if it's a positive aberration, we put in a negative aberration and basically cancel it out. We feel the analysis is only preliminary, but we're pretty optimistic that we can take out all the aberration with the second wide field camera and get us back to the original specification.
Nobody believed us, but we promised that we'd do it, and would do it by December '93.
Let me conclude by saying HST was and is a difficult challenge for a tremendous payoff.
Hubble became it was in the press all the time with the problems. It was a billion-dollar mistake. People in the press called it a technological disaster, a national disgrace. Late-night comedy hosts were making jokes about Hubble.
Well, have you been reading about the problems of the Hubble telescope? The Hubble Space Telescope?
The Hubble Telescope?
The Hubble Telescope is the Hubble Telescope.
Well, see, since there's no longer a Soviet threat, a lot of people feel we don't need the Star Wars defense system anymore. Hey, I think we should keep it, if only to shoot down that Hubble spacecraft and put this thing out of its misery. Huh? Yeah. Oh, that's what I say.
The teams at NASA, combinations with Johnson Space Center, Goddard Space Center, Space Flight Center, great astronauts, the will of the people, great members of Congress who supported it, said, let's fix it. We fixed other things, and they still work. Old cars still run. Let's make Hubble the better version.
We were all disappointed, but all hopeful that something might be done to save this spectacular space observatory. And in fact, something was done. We had already planned to be doing servicing missions on Hubble over the years, and so the first servicing mission to send astronauts back to Hubble was designed to repair this problem with Hubble.
And this big mirror really was the dominant driver. We worked very, very hard to develop, first of all, how distorted was it? How mispolished was it? And then to find a company in the United States, preferably, that could polish corrective lenses that would take care of the problem. Those two challenges were really immense, and those challenges, when they finally got solved, led to something that was an extremely important payoff to the U.S. and world citizenry.
To fly what you test and test what you fly would be easier if the telescope were back on Earth. But landing and relaunching could contaminate the telescope or damage it through vibration. NASA couldn't test the new corrective optics in the actual telescope. So to make sure the optics will work, the team had to determine the condition of Hubble in space and replicate that on the ground. One independent review panel used Hubble images to determine the precise shape of the flawed primary mirror and the prescription to fix it. Another team had to verify that the corrective optics will work. Teams had to test two optical packages, the replacement wide-field planetary camera and the corrective optics for the other instruments, called COSTAR. Engineers built several independent analyzers to test that they had replicated what the Hubble telescope does to light. For mechanical testing, engineers built a simulator at Goddard Space Flight Center using the same precision equipment that built Hubble originally. To replicate Hubble during electrical tests of the corrective optics package and the new camera, an electrical test facility was built with the same schematics as the original telescope. Hardware has been thoroughly tested on the ground. The Hubble servicing team is preparing for contingencies. But this mission is a first, so no one can predict everything that could happen. The real test will be in space.
5, 4, 3, 2, 1.
20.
And we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
Houston, Endeavour has a firm handshake with Mr. Hubble's telescope.
We copy that, Cubby, and there are smiles galore down here.
They got it. All right. Fantastic.
I forgot my glove.
Strange.
We're going to do whip pick on day 2 now. Sudden change of plan.
That's it. Change of plan.
No, I think if the arrays are straight, we also have an equal chance that there is no such thing as spherical aberration. The universe is aberrated, and we're going to be correcting for it.
Actually, also.
Okay, then you're seeing what would be the upper outboard bistem on the plus V2 array. There is a definite kink right at the upper edge of the second panel there, as you can see in the max part of the bend. And it looks like, as the bistems, of course, one is inside the other, it looks like the outer bistem has a kink in it, and it is also twisted approximately 90 plus degrees clockwise there at the kink. Then it looks like it all comes back together within a few feet there of the kink. There's also, probably hard for you all to see, we have to look at with binoculars, a second kink a couple of feet below the obvious one that is on the back side there of that section of the bistem. It's not quite as bad, but it does have a little crease in it.
Foot restraint will be occupied by mission specialist Kathy Thornton. She will be working from the end of the mechanical arm. This television shows Thornton at the array to be jettisoned.
Okay, KT. You ready?
Yeah, I'm ready.
Okay, they say you got to go for release. Expect 20 pulses on the RHC.
Hey, no hands.
It is going to be 20 pulses on the RHC for a set burn. Okay.
Almost like a bird, Tom. Look at it.
Look how stable you left that. There it goes.
Mars at 0.
Now you can see
It's like a
distortion.
I've got several places. We identified this pre-flight in case something like this happened. But we could go grab blankets and covers.
Maybe if we can have another EVA day like we did the first, and it looks like we're halfway there, we'll be well on our way to having a very, very successfully completed mission. So in fact, I remember after the first day saying that if we could just have 2 more like today, we'd be sure of great science. So it looks great.
The mirror, this is like the mirror in the wide field camera that's used to correct for the spherical aberration in Hubble.
And it's done by putting the same error on this mirror that exists on the Hubble mirror, only with the opposite signs. So the result is that after having the optical image distorted by the primary mirror, the distortion is removed by the secondary mirror. And the result is that you get a good clear image at the end.
I'm on it. Okay. All right, stop the arm. Stop the arm. Stop. Is the mirror clear? Yes, we're totally clear. We're ready to start in. Okay. Rod, let's come on in. Okay.
Nobody really believed they could do all of this work, and they did it, and did it in fine fashion. You know, even with some problems along the way. So that brought Hubble back to life, and it kind of took away some of the criticism of NASA, because they had now demonstrated that they could do something that had never been done before. We had never serviced a telescope. So when people talk about the legacy of Hubble, I think among its greatest legacies will be helping humanity understand that, yeah, when things go to space, we can, in fact, it's not hopeless if there's something wrong. We can service them in many cases if we make some preparation to do that.
Stop. Stop. Okay, here we go. I'm going to get the field. Put it on, the light comes on.
With the camera now installed, Claude Nicollier will reposition Jeff Hoffman so that he can now completely latch the new instrument into the telescope.
Right now it's looking very, very good that we've accomplished all we needed to accomplish for the optical correction of HST. And that's good news for astronomy. And it's good news for NASA to get over this little episode in our history.
And after 5 EVAs, spacewalks, the astronauts came home, and about 2 weeks later we took off the bandages from our eyes, and suddenly Hubble was fixed. It was totally fixed.
Is this it?
Hey! One to the bright
right
picture.
There!
Oh!
Did it!
Wait.
Oh, no, go.
Yeah, let's get
Yeah, bring it up. Yeah, bring it up.
Bring it up more.
Come on.
Oh.
Come on.
Not bad. That's it. There you go.
Well, can we get a sense for which is the brightest pixel?
Yeah, just run the cursor around in there.
Oh, there.
Oh.
It's 2 pixels.
Whoa. Not bad at all.
I chaired the subcommittee that financed the manufacture of the most significant contact lens in American history, the fix on the Hubble Space Telescope, and then bankrolled this extraordinary space HMO that went out and gave Hubble Telescope a new contact lens. And I'm happy to announce today that after its launch now in 1990, some of its earlier disappointments, the trouble with Hubble is over. We have here a picture taken of the image of a star with the new faint object camera. Here we have the picture taken prior to the servicing mission without the co-star. Over here on my left is the new picture taken of the same star configuration after co-star. This is the picture of the same galaxy, and then here is the picture taken of the same galaxy through the new wide-field planetary camera that was installed by our gallant and brave astronauts. The pictures are remarkable. The science that will come from the pictures are of historical significance. We will now, because of the Hubble fix, be able to do 21st century science that will enable us to look back on the universe. And this is only the beginning.
3, 2, 1. Ignition and liftoff. Discovery now on its way to service NASA's Hubble Space Telescope.
The Hubble Space Telescope is a magnificent achievement because it involves so many aspects of expertise and support, everything from engineering, technology, cultural support, scientific motivation, political support. It was also very innovative because it involved building on the technology developed through the Apollo program of NASA, and then advancing that to the point of having the space shuttle being able to carry satellites like Hubble into low Earth orbit, and then creating an infrastructure where you can bring astronauts repeatedly back up to an orbiting satellite, connecting with that satellite and having those astronauts go out in extravehicular activity to repair, service, upgrade that telescope, that satellite, and then let it go again to continue doing its science, inspiring future missions and future ways that astronauts and science and engineering can all work together to produce new advances in human space exploration. Hubble was pretty much the pioneer in this kind of sustained effort, and we should be grateful for it.
We have booster ignition and liftoff of the Space Shuttle Discovery on a mission to repair the Hubble Space Telescope as we venture into the 21st century.
I hope that it helps us understand what humans are capable of, period. I mean, Hubble represents so many different pieces of this planet working together in harmony. We've got the European Space Agency, NASA, all the universities and science organizations all around this planet that have a vested interest and have reaped the benefit of Hubble. Yeah, I certainly hope it's shown us what we are capable of.
Liftoff of Space Shuttle Columbia to broaden our view of the universe through the Hubble Space Telescope.
It took about 3 years of training before we were ready to go fly. The Hubble missions are some of the most complicated space missions we've ever attempted, and the repairs were difficult, involved developing new tools and procedures. And so that's why it takes longer for a Hubble Space Telescope mission than it did, say, for a International Space Station assembly mission. Those you could turn around much more quickly.
The loss of this valiant crew is something we will never be able to get over, and certainly the families of all of them, we have assured we will do everything we can possibly do to guarantee that they work their way through this horrific tragedy.
The final Hubble servicing mission that left Hubble as the observatory that it is today almost didn't happen because after Columbia, Sean O'Keefe was the NASA administrator, and he made the decision that Hubble was too risky.
I think we all respected the administrator at the time who actually came out in person to tell us. We didn't like what he was telling us, but at least he didn't just send an email. He came out and tried to explain his rationale, which was simply that he thought it was too dangerous for the astronauts since there was no safety net if something went wrong.
Hubble was in an orbit that the crew couldn't use the International Space Station as a safe haven if something went wrong. That, for all of the station missions, our plan was if we could just get the crew somewhere to orbit, we could get them to the International Space Station and put them aboard station until we could get another flight to come up and rescue them.
But so we fortunately were able to keep people occupied while this was churning through the system, and we did some very good work on the possibility of robotic servicing of Hubble. And after a year's worth of work, we actually decided that it would be possible in the future, but we didn't think we could develop it in time to actually be useful for Hubble before it lost control or wasn't able to observe. Unfortunately, about the time we had decided that is when the new administrator came in and said, let's find a way to make the final servicing mission happen.
Just under 3 years ago, NASA had to announce a very troubling decision, that decision being to cancel shuttle servicing mission 4 for the Hubble Space Telescope. And today I'm here to announce a much more pleasant decision on behalf of the agency. We are going to add a shuttle servicing mission to the Hubble Space Telescope to the shuttle's manifest to be flown before it retires. We anticipate
the public response was probably as important, if not more so, than the professional astronomical community's response. I mean, both wanted to see Hubble service, both wanted to continue, but the public, in some ways, was our savior. I mean, they went and they talked to their Congress people, they wrote editorials for newspapers and everything, and there are a lot of people on the Earth, the youngsters, have never known a time without Hubble in the sky. And they just didn't want to see it go away. So I think their investment in it, their connection to it, coupled with the way they were able to describe that to the media, to Congress, whatever, it really got through to people and to the administrator and said, this is important for more than the science. So let's find a way to make it work. And we did.
Seven, 6, 4, 2, 1, and liftoff of Space Shuttle Atlantis. Final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Bypass across the board, Scooter, no way. You over the top? Yep. Okay, you're doing a great job. Thanks. Roger. Ready, John. And there's at the labyrinth field. Fantastic. You want to increase your rate slightly? Increase rate, Megan.
Copy, increasing the rate.
John, could you get a diver to hold up the mirror end? Sure. The mirror is just outside of the telescope. The mirror is 1 foot outside the telescope. Okay, increase rate, Megan. John,
Copy.
Clear for the maneuver. You're clear for the maneuver. Go for the maneuver, Megan.
Copy, going to aft fixture.
I'm the witness on this. You actually were the last guy to pat it goodbye. What were you thinking when you patted Hubble goodbye? What was going through your mind?
Happy voyages. I hope everything that we did worked. It's hard not to think of Hubble as something alive, but I really was thinking of Hubble as a friend.
This is a really tremendous adventure that we've been on, a very challenging mission. Hubble isn't just a satellite. It's about humanity's quest for knowledge. As Arthur C. Clarke says, the only way of finding the limits of the possible is by going beyond them into the impossible. And on this mission, we tried some things that many people said was impossible: fixing stiff, repairing ACS, achieving all the content that we have in this mission. But we've achieved that, and we wish Hubble the very best. I want to wish Hubble its own set of adventures, and with the new instruments we've installed, that it may unlock further mysteries of the universe.
Repaired the 2 failing instruments, put in 2 new ones, replaced gyros, a whole bunch of things, really massive mission, and did such an excellent job that we're here more than 10 years later now, and we're as capable as we've ever been. Things are still working. We've lost a few gyros, but we still have enough to operate on. All 4 of the instruments that were alive after the servicing mission are still going strong. We are supremely grateful for getting that last servicing mission in, because we would not still be operating at this point if we hadn't done that. That allowed us to get the telescope in a configuration for maximum following lifetime.
It's about newness. It's about challenge. It's about going out there in the forefront of technology and breaking through. And Hubble represents that to the greatest degree that I can think of, because it allows us to do it in a big way and in a small way. It allows us to do it in detectors. It allows us to do it in computer technology, in optical fabrication, and optical polishing. But it also gives us this big picture. It also gives us this great challenge of making things better.
A lot of people say they feel very insignificant when they look at these images that show thousands of galaxies and tell us that there are hundreds of billions of galaxies beyond the Milky Way. And that's a certain understandable response. But I also feel a sense of gratitude and even significance myself. Now, these are philosophical issues, not science issues, right? But I feel a sense of significance that we as humans have developed or been granted the ability to develop instruments that enable us to see far beyond what the human eye alone could ever see, and to think about what it means, to think about how we on this planet relate to star systems far beyond our own. I think that's wonderful. It should make us all feel a sense of gratitude and humility, and also connectedness. You know, we're on different sides of a planet, but we're all connected as human beings on planet Earth as part of this magnificent universe. I think it should and does have a unifying effect for humanity, and I'm grateful for that.
Imagination is great, but execution is everything. So, okay, we can imagine being able to see the cosmos, and that's great. And great astronomers, great thinkers, wrote the governing equations, they imagined it. But what did it take to be able to do it in a way that responds to what we learn in a way that allows us to go beyond just the framing questions, you know? And so, the Hubble Space Telescope is the consummation of a masterpiece of engineering, because many of the things Hubble did and continues to do were miracles of engineering that did not exist before. Hubble expanded our horizons of thinking with an engineering solution to something that changed the way we viewed space. Space all of a sudden was beautiful. It wasn't just equations that say, well, there's something, event horizon like a black hole. Look at Hawking's work and, you know, and Einstein's and, you know, others. It's more than that. It's beautiful, it's elegant, it's populated. It's not just light from stars. It's connecting glue. It's the, you know, it's grand challenges. It connects other galaxies to suns, to planetary systems that we can indirectly sense. All that took a space telescope to do, and it had to be a good one. Hubble discovered things that are now fundamental in the astrophysics of our universe. Oh my God. But the millions of engineering solutions that let it work, it's, you know, they're beyond words. They're magic. I think that's why it was so transformative in space science. It brought space science to the people because it talked about all space. And it stared at key places in all space to tell us what could be. And that is brilliant. You know, space is a tapestry. It's a mosaicism of stuff. Some wish we can't see. Hubble saw a lot of it and showed us how to look at it differently. And that, I think, is its legacy.
Humans are very good at kind of putting our hearts and souls into things that are made of just metal and wiring. I mean, think about perhaps the connection you might have to your car. You know, your car is something that is used by you every day, is touched by you. It may have a personality to you. It may feel very secure, or it may be very contentious. It's always breaking down. It's natural for us to sort of put ourselves out into the world in things that might not really be conscious, that are just machines. And when you hear the Hubble Space Telescope, you think of something, well, okay, it's a telescope. It's a big metal tube. We launched it up into space. It's very far away. They're seeing things that are very esoteric that I wouldn't understand. The thing I would ask you to do is just take a little time and look at some of these pictures, because if the artistic merit of what a giant cloud forming hundreds of stars looks like, even if you don't really understand what that is, start by just looking at these beautiful pictures and then start reading. We go through a lot of trouble. Our wonderful science writers are trying to describe what you're really seeing, the drama of it, the scale of it, and also the connection. You know, you're looking at a place where our sun, our solar system, and your body literally come from these places that Hubble's taking a picture of, these giant clouds, making every chemical element that there is in the universe. You are part of this story. And I know that can seem hard. Scientists can seem like very distant people, very different from the rest of the world, and we're completely not. You know, scientists are you. Scientists are your neighbors and your friends. And if you've ever asked a question, you know, or if you've ever looked up into the night sky with wonder, you know, you're one of us. You know, you get to be included along with the scientists. Hubble is to us a piece of machinery that we have put our hopes and our dreams and our PhD dissertations and our arguments and our frustrations into. And 30 years on, you know, this one metal cylinder up in space carries the souls of tens of thousands of people. And, you know, that's something that it's a wonderful part of being human. What we touch begins to carry part of our humanity with it.
Congress wasn't at all sure that it wanted to pay for the Hubble. And it took really a major effort on the part of the astronomical community to lobby Congress to get the final funding approved. Now, Proxmire, who was you may not want to use this story, but I think it's a good story.
I'd love to hear it.
Proxmire was noted for the fact that laughing at the ways government wasted money. And he sent a question to NASA headquarters saying, why should the American taxpayer pay for something like the Hubble? And I did a back-of-the-envelope calculation, and my answer was that for the cost of a night at the movies, every American taxpayer would have 15 years of exciting discoveries. And I may have been off by a factor of 3 or 4, depending on how you figure launch costs and the servicing missions and some other things. But even if it ended up being one night at the movies every year, I think Hubble has been worth it.
Hi, I'm Alvin Drew. I'm an astronaut. This is Ask NASA, and I'm here to answer your questions. So who is going to the moon with NASA? It's going to be a lot of folks. It's going to be our own industry helping us get there. It's all going to be our international partners, many of whom have been with us on the International Space Station, plus a few others. Who's building the Gateway? Well, for those of you not familiar, this is the Gateway. Lots of folks are going to build this. Different companies are going to build these things. Different countries are going to contribute. This part here with the legs on it is the part that takes off and lands from the surface of the moon. And then finally, this is a transition stage to get us across that 50,000-mile gap between the Gateway and the moon. The Gateway is a great place for us to stay on the moon. And so if you have a vehicle out there that can dock to it, no matter what it is, no matter what country you're from, you can plug into it. You can get power, you can get data, and then you become part of the Gateway. The Gateway will work a lot like the International Space Station. We'll assemble it using robotic arms and spacewalks as well, along with docking and berthing, just like we do today. Why does NASA need partners? Well, it's because we're doing great things out there. We're not going to go anywhere without our partners with us. It's going to take a crew to get us to Mars. Another example of our international partnership is the International Space Station. 19 nations in total is what it took to make that space station is what it is today. So what's the next question here? Is this a modern space race? Well, yes and no. Yes, we're up against the clock, but no, we're not racing against each other. This is more of a partnership, a relay race that involves our domestic industry as well as our international partners. So how did going into space influence you? It's a tiny, tiny little island in the middle of a great big black sea. There's no little yellow boundary line separating our countries from one another. We really are all together here on this one island in the middle of nowhere.
That was the best throw we've ever had, I think. So what does it feel like in space?
You're weightless, you unstrap from your seat, and you can float. Imagine being in a pool without any water, you're not wet. What's the best way to become an astronaut? I can tell you the one thing every astronaut had in common is that they were pursuing something that was not being an astronaut, that really had their passion. They really liked what they were doing, and that's why they excelled at it, and that's why they stood out enough to become an astronaut.
Where can you find the best views on the International Space Station?
From the cupola, far and away, the best investment we've ever made. You can just see the universe from there, short of going out on a spacewalk.
I heard you were in a Willie Nelson video. Do you still have your costume?
Of course I still have my costume. What else do you think I'm wearing when I'm playing air guitar? One of the cool things about being an astronaut is you can sometimes inadvertently wind up on the set of a video shoot. This one involved Willie Nelson and his Whiskey River Ranch. Well, Alex, I can only guess. We're going to go to Mars here in the near future. We're going to go to the moon in preparation for going to Mars. And by the time we get there, you'll be old enough to come back and tell me what life was like on Mars. To the top, where there's the best view.
Do you have a question for NASA? Send your questions to our experts on Twitter using #AskNASA.
Through Artemis, the twin sister of Apollo, we are returning to the moon. This is Orion, the only human-rated spacecraft in the world capable of deep space travel. And now, the Space Launch System, NASA's most powerful rocket since the Apollo era, stands ready. Having undergone and passed numerous tests, the time has come to complete the journey. With hardware originating from every state in the nation and from partners around the world, Artemis 1 will be the first flight test of each of these components now assembled together. These two solid rocket boosters will provide more than 75% of the thrust necessary to leave Earth. Each booster stands 17 stories tall, a full segment more powerful than the SRBs of Shuttle. Together, these boosters are capable of 7.2 million pounds of thrust and will burn for the first 2 minutes of flight. The core stage, at 212 feet, is the tallest rocket stage NASA has ever built. With the rocket's flight computer secured inside, the core stage is designed to hold 2.3 million pounds of fuel. The 196,000 gallons of liquid oxygen and the 537,000 gallons of liquid hydrogen will combine to provide 8.5 minutes of propellant to the 4 massive RS-25 engines mounted below. As proven workhorses of the shuttle fleet, each RS-25 engine has a legacy all its own. Together, these 4 engines provide 2 million pounds of thrust, and with the SRBs, are capable of pushing Orion to a speed of 17,000 miles per hour. The interim cryogenic propulsion stage is a 45-foot tall upper stage that offers Orion nearly 25,000 pounds of thrust. Performing 2 separate burns, the ICPS will first raise Orion's orbit and then, later, propel it out on a trajectory to the moon. The ICPS is powered by a single RL-10 engine that will perform these 2 burns. This storied engine has propelled robotic missions to every planet in the solar system, including Voyager 1 and Voyager 2, the first space probes to reach interstellar space. Orion's service module, provided by the European Space Agency, is the powerhouse that fuels and propels Orion in space. It stores the spacecraft's propulsion, thermal control, electrical power, and critical life support systems, such as water, oxygen, and nitrogen. Orion's crew module is the pressurized segment of the spacecraft, where future crews will live and work on journeys to the moon. Capable of accommodating 4 crew members for up to 21 days, this capsule includes state-of-the-art avionics, innovative crew systems, and the largest heat shield of its kind for entry back into the Earth's atmosphere. Positioned at the top of Orion is the Launch Abort System, designed to pull the crew to safety in the event of an emergency, on the pad or during launch. 3 solid rocket motors can activate in milliseconds, accelerating from 0 to 500 miles per hour in 2 seconds to propel Orion and crew safely away from the rocket. Now fully assembled, Artemis 1 stands at 322 feet. Artemis is no longer a series of separate parts and programs. United together, this is the first of Artemis's arrows, capable of ushering in the next chapter of human lunar exploration. Only together, this mighty system represents all that is possible, all that we are capable of when united around a stunning vision, with each component playing its part in a grander effort. We, the people of NASA and our partners, we, the people of the Artemis generation, all around this beautiful world, will bear witness to what we are capable of. Together, we are going back to the moon.
May 5th, 1961, Freedom 7. The United States took the first small step on its journey to the moon. America's first man in space, Alan Shepard, rode the Mercury capsule. Lifted to 116 miles by the Redstone rocket's 78,000 pounds of thrust. 10 years later, the launch vehicle is Saturn V, with a thrust of 7.5 million pounds. On January 31st, 1971, the crew of Apollo 14 would leave Earth on their mission to the moon. The man who began our first decade of manned spaceflight would command the mission that would close that decade. Alan Shepard. With him, Stuart Roosa, who would orbit the moon alone while Shepard and Edgar Mitchell explored its surface. Their destination, a rugged area of lunar highlands called Fra Mauro. Apollo 13, aborted as it neared the moon, had been unable to land at this site. Now, we were trying again. But why Fra Mauro?
What happened to the moon during its first billion years
a period erased on Earth. How do the Earth and Moon differ in overall composition? By visiting Fra Mauro, we hope to sample the very bedrock of the Moon, material very different from that so far collected, material perhaps dating back to the beginning of the solar system.
How can you think of the soil being 4.5 billion years old when igneous rocks which presumably underlie it are only 3.5 or 3.7 billion years old?
This, I suppose, will be dramatically refuted or confirmed at the Apollo 14 mission when they actually visit Fra Mauro.
Most of the activity is associated with one place on the Moon, and we have tentatively located that place in or near the crater Fra Mauro.
Everything went smoothly during Earth orbit and for the burn that sent Apollo 14 toward the Moon. Then Stuart Roosa moved the command module Kitty Hawk to a docking with the lunar module Antares, still attached to the third stage of the booster.
And we docked. We're unable to get a capture.
Twice they tried. 3 times.
Okay, Houston, I hit it pretty good and held 4 seconds on contact, and we did not latch.
Roger. We're seeing it all on TV here.
Well, we better back off here and think about this one, Houston.
As the astronauts waited, an identical docking probe was brought into mission control. This probe on the command module fits into a funnel-like device on the lunar module called the drogue. Tiny catches on the probe's point engaged the drogue. It was these capture latches that were not holding. In space, the astronauts tried a 4th time. And a 5th.
No latch. No latch, Houston.
Roger.
In space, on Earth, they searched for a solution. Then, on the 6th try,
I believe we got a hard dock, Houston.
as they coasted to the Moon, the crew brought the probe inside the spacecraft for examination. On Earth, the probe was tested and retested, for we had to be sure that the probe would work for the most critical docking, as Shepard and Mitchell returned from the lunar surface. On February 4th, Apollo 14 went into orbit around the Moon.
This is really a wild place up here.
As Apollo 14 was on its first orbit, the third stage of the booster smashed into the Moon at its planned target point. Its impact picked up by the seismometer left by Apollo 12. The structure of the Moon's interior is one of the major mysteries of lunar science. Now another piece was added that could help solve the puzzle. Later that day, Shepard and Mitchell climbed into the lunar module Antares and undocked prior to descent.
And we're free.
Beautiful. Very good.
But as they checked out the lunar module, a problem appeared. An erroneous abort was being signaled on board Antares and in mission control. Should this occur during the landing burn, Antares would abort automatically and the landing would be off. The mission control team had 2 hours, the time of one lunar orbit, to find a solution. Flight controller Dick Thorson diagnosed the trouble as a loose particle in the abort button. The burden then came to rest on the shoulders of computer programmer Donald Iles. Working against time at MIT and Cambridge, Massachusetts, he reprogrammed the lunar module computer to ignore the false signal. This new program was then checked out in a simulator at Cape Kennedy. As Antares came into contact with Earth again, the instructions were sent up to the crew.
Antares, Houston, the computer's yours.
Thank you. You troops did a nice job down there.
That was beautiful.
Less than 10 miles above the lunar surface, Shepard and Mitchell swept across the landing site.
And Antares, Houston, your go for Morrow.
It's a beautiful day to land at Morrow.
Then, another problem. The landing radar, which would tell them their altitude above the lunar surface.
On radar. On radar.
Antares, Houston, would like you to cycle the landing radar breaker.
Okay, cycle.
Okay, I would like to accept the radar.
Switching through. Great. Great. That was close.
Okay, and monitor descent fuel.
I'm starting the camera.
10 seconds to go.
Okay, there's pitch over.
Right on
and there it is.
Right on the money.
Right on the money.
That's beautiful.
Right out the window, just like it should be.
Antares, Houston, your go for landing.
Cone Crater, a major objective of this mission to Fra Mauro. A hole blasted in the moon's surface eons ago that could provide a scientific clue to the history of the moon, the Earth, and the solar system.
Right on schedule. Right on schedule now. Went back Cone Crater right outside to my right.
We think that the Fra Mauro area was formed from material thrown out by the impact that created the Imbrian Basin to the north. If this is the case, we could get samples torn out from as deep as 60 miles in the lunar crust. All in all, the Fra Mauro material should contain a great deal of new information about the early history of the moon, and thus help us to better understand the formation of our own Earth.
Okay. Okay, I'd give it a few clicks. You're through 200 feet. 5 feet per second. That looks good.
No metal here.
9% fuel looks great. Okay, looks like you're going right over the middle of Triplet. You're 170 feet out, 2 feet per second down, 8% fuel. You're looking good. Okay, you can move on forward. You're just barely crossing North Triplet. Barely crossing North Triplet. You can land over here. There's some dust, Al. You're on your own. It's
Starting down. Starting down.
okay. There's good dust. Crossing down. Looking great.
60 seconds.
40 feet. 3 feet per second. 30. 3 feet per second. Looking great. 20 feet. And 3 feet per second. Contact now.
News stop. Auto.
We're on the surface.
Okay, we made a good landing.
Roger, Antares.
5.5 hours later, Shepard left the lunar module to begin the first of 2 explorations.
Starting down the ladder.
Roger.
10 years later, 114 hours, 22 minutes after leaving Earth, Alan Shepard stepped onto the moon.
It looks like you're about on the bottom step and on the surface. Not bad for an old man.
Okay, you're right. Alma's on the surface, and it's been a long way, but we're here.
4 minutes later, he was joined by Ed Mitchell.
The last one is a long one.
Following the tradition of 2 previous missions, Shepard and Mitchell planted the flag in the lunar soil.
How's this, Bruce? Look okay? Roger, that's a good sight.
The next job was to load the Met, a rickshaw-like wagon the astronauts would use to transport their tools of exploration and collected samples.
One of the big factors in lunar exploration is mobility. In Apollo 14, we had the Met, which let us move further afield than the previous 2 missions. In future missions, we'll use the lunar rover, a sort of moon-going dune buggy. This mobility will mean less time spent in getting from here to there and more time collecting scientific data.
Okay, I'm going to stop here and rest for a minute now. Let's turn things heavier than I expected.
Shepard pulled the Met while Mitchell carried the barbell-shaped package containing an automatic scientific station they would assemble. A station designed to continue broadcasting data to Earth for a year after men departed Fra Mauro.
Okay, Houston, we're proceeding over a very fine grain regolith we described before. Good heavens, that's a deep hole. Going down in a depression. Deep, very deep depression. That is what it looked like.
Right here, you're visible from about the armpits up right now.
Nothing like being up to your armpits in lunar dust.
Finding a suitable site to place the scientific instruments was the next order of business. Shepard and Mitchell now began setting up the automated scientific laboratory. A small nuclear generator to power the array. The central station to transmit data to Earth. A seismometer to detect and measure activity on and within the moon. A series of 3 experiments to measure charged particles near the lunar surface. An independent experiment to reflect laser beams from Earth, enabling extremely precise measurements of such things as Earth-to-moon distance, the wobble of the Earth's axis, continental drift, and shifts of the Earth's crust. And a mortar to be fired by a signal from Earth sometime within the next year. The impact of its charges would be picked up by Apollo 14's seismometer. As a final exercise, Mitchell used the thumper, a device to explode a series of controlled shotgun-like charges. The vibrations from these detonations were picked up by a series of instruments he had previously deployed. With the instruments set up and operating, they headed back toward Antares, pausing on the way to collect samples. They loaded their 44 pounds of lunar material aboard the lunar module, and after 4 hours and 50 minutes on the surface, climbed back into Antares. As Shepard and Mitchell rested, Stuart Roosa continued his work from lunar orbit. His photographs would have meaning not only to the scientific community, but would have direct bearing on the planning for coming missions.
Yeah, it's nice to be up. A sunny day again. Yeah, it's a beautiful day here at Fra Mauro Base.
12 hours, 40 minutes later, Shepard and Mitchell began their second exploration period. After loading the lunar rickshaw, Mitchell began the journey to Cone Crater. Shepard adjusted the television camera, then hurried to join his partner.
Okay, Houston, we're headed just about toward the center of Cone Crater. Okay, point A, Al, is right. It's not quite in the valley, it's right beyond over here. Okay, this is probably pretty good.
Point A, the first stop on the trip to Cone. Here they would collect and document samples, measure the local magnetic field, and take core tube samples from beneath the surface layer.
This is a good place for A. They have an appearance here quite often like raindrops. A very few raindrops have splattered the surface.
The quality of the scientific description by the astronauts could be termed by Earth-based scientists only as excellent. But now Shepard and Mitchell pushed on, After a brief stop at a second survey site, they began their assault on Cone Crater, a climb not only toward the summit of a lunar mountain, but back through time.
A large crater acts in many respects like a drill, throwing out material from deep beneath the surface. This material should be very different from any we've collected before, perhaps dating back to the origins of the moon and even the solar system.
And we're starting uphill now. Climb's fairly gentle at this point, but it's definitely uphill. Why don't we pull up beside this big crater? Okay, take a break, get the map, see if we can find out exactly where we are.
The maps they were using had been made from photography from lunar orbit. The hummocks, craters, ridges, and boulders took on a new appearance when seen from the surface.
The little limb looks like it's got a flat over there the way it's leaning. Start on up toward the rim? Yeah, just 1 second though. Hey, pull a while out. We're having all the fun. And the grade's getting pretty steep. Al's got the back of the mitt now, and we're turning it up. I think it seems easier. Well, I tell you, we're really going to get a panorama. We got a tremendous one here, Houston, already. And we're not quite to the rim. But the rocks and boulders get more numerous towards the top here. Okay, well, now that's apparently the rim of Cone over there. And we're about almost 2 hours now. That's at least 30 minutes up there. It's going to take longer than we expected.
Now they were working against time, against the oxygen and water left in their backpacks, against the alien terrain. Top a ridge, thinking it's the rim of the crater, and there's another ridge ahead of you.
I don't think we'll have time to go up there. Oh, let's give it a whirl. Gee whiz, we can't stop without looking in the Cone Crater. Okay. Well, press on a little further, Houston, and keep our eye on the time.
Okay, and so right now we have a 30-minute extension.
Looks like we'll be approaching the rim here very shortly. Okay, we better reconnoiter here. I don't see the crater yet.
Standing in a boulder field surrounded by rocks 10 to 12 feet long, the astronauts made their most difficult decision. With the concurrence of Mission Control, they stopped their climb, less than 150 feet from the edge, to begin the more important job of collecting samples.
The crew had no way of realizing they were so close. It was a week after the mission before we determined this by photographic analysis.
While they could overcome the terrain, they could not beat the steady drain of oxygen from their backpacks. In the terms of scientific meaning, the decision not to go on to the rim meant little. In human terms, a great disappointment.
One of these boulders, Fredo, is broken open. They're really brown boulders on the outside. The interface that's broken is white. And there's another one that most of it is white. They're right in the same area.
The white rock is of different composition to the Apollo 11 and 12 rocks. In fact, the chemistry of all the rocks that have been looked at so far is different to those rocks. Potassium and uranium are 10 times higher, which are the sort of values we might expect if the Fra Mauro rocks represent ancient lunar crust, which of course is what we're all hoping.
Again, it was time. Time to head back to the lunar module.
Approaching the rim now. Coming into Fra Mauro base.
After a quick side trip to check on the science station, they loaded the lunar module with samples and data and stepped off the lunar surface. The second expedition had lasted 4 hours and 35 minutes, a total exploration of a record 9.5 hours. 33.5 hours after they landed, Alan Shepard and Edgar Mitchell lifted off in the silent vacuum of the moon.
Gas and engine is armed. 6, 5, 4, 3, 2, 1, 0. We have ignition.
What a liftoff.
And liftoff.
Roger, ignition.
There's pitch over. 10 seconds.
Roger.
Hey, baby. Pitch over is good. Steering looks good, Houston.
Roger, you're looking good from down here, Al.
Coming up on 1 minute.
Half an hour later, Stuart Russo watched their progress from Kitty Hawk.
What are you doing way down there, oh fearless one? You've lost a little weight since the last time I saw you. Houston Antares, the station's keeping at about 100 feet, closing in a little more for the pictures of the service module and command module. Okay, shall do a loop later. Okay, make it smooth. And around we go. Show us a little style. Oh, you look good. There I was at 240,000 coming over the top.
That's our home away from home. Would you believe 360,000? Yeah.
Kitty Hawk is doing an extremely smooth loop. We're sitting at 70 feet, watching him go around. He looks very clean.
The inspection complete, Antares and Kitty Hawk moved together for docking.
Apollo 14, this is Houston. Here, go for the docking. Roger, we got you.
Okay, we captured. And we got a hard dock.
That big sigh of relief being breathed around here.
They transferred the gear from Antares to Kitty Hawk, buttoned up the tunnel, then jettisoned the lunar module. It would crash into the moon at a predetermined spot. Its impact picked up by their seismometer and the seismometer left by Apollo 12 over a year earlier. 149 hours after they left Earth, they performed the burn that broke them out of lunar orbit. During the coast to Earth, there would be time to catch up on sleep, relax, and do all the little things left undone. And there was one more item, a series of scientific demonstrations in zero gravity, demonstrations impossible to reproduce on Earth. These trials looked at basic physical properties of matter in zero gravity, studies that could lead eventually to new materials manufactured in space for use on Earth. On February 9, 1971, 9 days after they left Earth, the crew of Apollo 14 hit the atmosphere of their planet at a speed of over 24,000 miles per hour. They hurtled toward Earth, a meteor heading home. On board, 95 pounds of the moon.
Extremely important. It relates to the question of why we're fooling around with the moon. It's really that the imprint of history, of solar system history, on the Earth-Moon system is centered on the moon for the first billion years.
What do we hope to gain is we've got a window right now between t equals 0, the beginning of the solar system, and when the Earth so totally messed up itself that we can't look at it anymore. We'd like to look in there, and that window's on the moon.
Apollo 14 has already had a very big scientific impact, and we still have 3 missions left. They'll be heading into even more rugged and more interesting areas of the moon. Beginning with Apollo 15, the lunar rover will let us range further afield and collect more and more varied scientific samples and information. The study of the moon and how, for instance, elements and minerals are distributed in its crust will enable us to learn more about the process of crust formation on Earth, leading to a better understanding of the way that certain elements concentrate in the crust. Will we have had enough missions to the moon by the end of the Apollo program? Probably not. You can never have enough knowledge, but at least it's an excellent beginning.
En la NASA, nuestro recurso más importante es nuestra gente.
Una fuerza laboral talentosa, diversa,
dedicada a estudiar los secretos del universo y de nuestro planeta natal.
Para el beneficio de la humanidad.
La comunidad hispana contribuye a diario a misiones esenciales de la agencia.
Trabajando para mantener seguros a nuestros astronautas y misiones en órbita.
Monitoreando los efectos de cambios climáticos.
Prediciendo eventos meteorológicos que pueden afectar a nuestras comunidades.
Ayudando a la respuesta en desastres.
Diseñando los aviones de tecnología sostenible del futuro.
Desarrollando ciencia y tecnología a bordo de la Estación Espacial Internacional.
Desentrañando los orígenes del universo.
Buscando señales de vida antigua en otros planetas.
¡Hemos llegado! Perseverance llegó, y preparándonos para llevar a la primera mujer y a la primera persona de color a la Luna.
Nuestra diversidad de orígenes y culturas impulsa nuestra capacidad para innovar.
Y hace que nuestra agencia sea más fuerte, incluyente y diversa.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos NASA.
Sigue nuestras historias en NASA en español.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
All is in readiness for the launch of Apollo 11 from Cape Kennedy. Mission Control at the Cape reports the countdown is proceeding on schedule. Astronauts Armstrong, Aldrin, and Collins have suited up and ingressed the command module aboard this 363-foot-high Saturn Apollo configuration. Weather is satisfactory at the Cape. It is estimated that about 1 million tourists are now converging toward the beaches for the launch.
12, 11, 10, 9, ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Okay, we got a roll program. Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on a proper heading. Plus 30 seconds. Roll complete and a pitch program.
Altitude's 2 miles.
Oh, 11 Houston, you're good at 1 minute.
Downrange 1 mile, altitude 3-4 miles now. Velocity 2,195 feet per second.
Plus 135, 003, 554487. Minus 05484, minus 4 balls 1, plus 66232. You with me? Go ahead. 180-239-001. Apogee is NA, perigee is plus 00175. 66458-737, 661-9er. 24-2087-167. Foresight stars shallow. Left 008 down 27 minus 2605 minus 02500. 11229er 339er 0125535. Still there? Keep going. Okay, Den up in Vegas 067283 337 no LH. PLI plus 4 006.
Out there you see the orbital elements again. Apo. That's the altitude first. This is John Wharton, who operates this computer. It's all going Gemini 4s and he does.
Madrid AOS. Madrid AOS.
Early communications was noisy but readable. Mission Control was able to hear the voices of the crew shortly after the tracking station at Madrid, Spain, acquired the telemetry signals.
Apollo 11 is getting its first view of the landing approach.
The Apollo 11 lunar module Eagle has begun its descent toward the surface of the moon. The descent stage engine of the Eagle was fired at about 9 minutes after 2 p.m. Central Daylight Time. The engine burn time was less than 29 seconds. The engine firing places the lunar module into a slowly descending orbit. Meanwhile, astronaut Collins in the command module Columbia maintains a constant vigil on the descending lunar module. Communications have remained good with both Eagle and Columbia. The planned touchdown is for 3:17 p.m. in an area called landing site number 2.
30 feet down, 2.5. Picking up some dust. 30 feet, 2.5 down. Straight shadow. 4 forward. 4 forward, drift into the right a little. 1.5.
Showing the actual position of the spacecraft on the world map, and you can see Cape Canaveral has started tracking, and we will start processing that data.
Okay. Contact light. Okay, engine stop. APA at a descent. Mode control both auto, descent engine command override off. Engine arm off. 413 is in. We copy you down, Eagle. Listen, Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
The lunar module has been on the moon since 3:18 p.m. Central Daylight Time, following a near letter-perfect descent and landing. The lunar module, while on the surface of the moon, is being referred to now as Tranquility Base. Astronaut Neil Armstrong and Buzz Aldrin are preparing to step onto the lunar surface this evening. Preparations for the extravehicular activities are running a little behind schedule. A special display has been set up in the auditorium of Building 8 at the Goddard Space Flight Center during the flight of Apollo 11. A wide variety of displays includes models of the Apollo 11 command module and lunar module, an animated Apollo 11 mission profile, and information on the manned space flight network, the vital communications link required for the Apollo missions. Goddard employees are invited to bring their family and friends to see the display. Hours of the open house are from 10 a.m. until 8 p.m. daily throughout the Apollo 11 mission. In addition, visitors may watch operations of the real-time computer center, NASCOM and SCAMA through the viewing windows in Building 14.
NASA brings together the scholars and scientists of our university, the research and technological skill of our great industry, the will of the people, and focuses them on whatever job needs to be done. You are inside the lunar module, the LM or LEM. The craft is flown from a standing position, the LEM pilot to the right, the command pilot to the left. These are the commander's controls. His right hand is on the attitude controller, regulating pitch and yaw and roll.
Astronaut Neil Armstrong and Buzz Aldrin are preparing to step onto the lunar surface. Armstrong will leave the cabin first. TV viewers around the world will be able to see Armstrong be the first human to set foot on another celestial body.
Goldstone, Apollo.
Goldstone, Goddard voice. Would you maybe on net one for voice check, please?
Oh, roger.
Okay, I just checked getting back up to that first step. That isn't collapsed too far, but it's adequate to get back up.
Roger, we copy.
It's a pretty good little jump.
Buzz, this is Houston, F2, 1/160th second for shadow photography on the sequence camera.
Okay. I'm at the foot of the ladder. The LEM footbeds are only depressed in the surface about 1 or 2 inches, although the surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. Ground mass is very fine. That's one small step for man, one giant leap for mankind.
That's one small step for man, one giant leap for mankind.
Surface is fine and powdery. I can pick it up loosely with my toe. It does adhere in fine layers.
Honeysuckle, Goddard voice, net 3.
To the sole and inside of my
Roger, honeysuckle. How's your TV looking now?
I only go in
Roger, and we're starting to get the commercial picture now, thank you.
but I can see the footprints of my boots and the treads and the fine sandy particles.
White House, Goddard voice.
White House.
Roger, White House, Goddard voice. How do you hear me?
You're loud and clear, sir. How may?
You're loud and clear also. We'll be extending this circuit now into the Apollo net at Goddard for the presidential call to Tranquility Base.
Roger, thank you.
Thank you. Goddard voice out.
The view of the camera for a minute. Neil and Buzz, the President of the United States is in his office now and would like to say a few words to you. Over.
That would be an honor.
Go ahead, Mr. President. This is Houston out.
Hello, Neil and Buzz. I'm talking to you by telephone from the Oval Room at the White House. And this certainly has to be the most historic telephone call ever made. I just can't tell you how proud we all are of what you... For every American, this has to be the proudest day of our lives. And for people all over the world, I am sure they too join with America in recognizing what an immense feat this is. Because of what you have done, the heavens have become a part of man's world. And as you talk to us from the Sea of Tranquility, It inspires us to redouble our efforts to bring peace and tranquility to Earth. For one priceless moment in the whole history of man, all the people on this earth are truly one. One in their pride in what you have done, and one in our prayers that you will return safely to Earth.
Thank you, Mr. President. It's a great honor and privilege for us to be here representing not only the United States, but men of peace of all nations, and with interest and a curiosity and with a vision for the future. Honor for us to be able to participate here today.
And thank you very much, and I look forward, all of us look forward to seeing you on the Hornet on Thursday.
Look forward to that very much, sir.
Columbia, this is Houston, over.
I think it's a little difficult to dig through the initial crust.
Very interesting. It's a very soft surface, but here and there where I plug with the contingency sample.
Two groups at the Goddard Space Flight Center are waiting for samples of the moon rocks that will be brought back by astronauts Armstrong and Aldrin. The scientists, headed up by Dr. Isidor Adler of the Theoretical Studies Branch and Dr. John Philpotts of the Planetology Branch, will be among some 140 experimenters from the United States and foreign countries to receive the samples after they have gone through quarantine and prepared for distribution by the Lunar Receiving Laboratory of the Houston Manned Spacecraft Center.
Samples out here, the hard rock samples, have what appear to be vesicles in the surface. Also, I'm looking at one now that appears to have some sort of phenocryst.
Hey, Neil, didn't I say we might see some purple rocks?
Find the purple rocks?
Yep.
At approximately 11:53 p.m. Central Daylight Time tonight, astronauts Neil Armstrong and Buzz Aldrin began preparations to re-enter the lunar module.
The Eagle lifted off the surface of the moon at 12:54 p.m. Central Daylight Time today.
Apollo 11 is on the way home.
Apollo 11 is streaking toward a splashdown in the Pacific Ocean. The speed will rapidly increase to a maximum of about 24,800 miles per hour. 400,000 feet above the Earth, the spacecraft will begin to encounter the atmosphere. At that point, the heat shield will begin to heat up.
506, this is Sydney. Go ahead.
Good morning, ladies and gentlemen. Captain Brown speaking from the flight deck of Qantas 596. It does seem that we're going to get a very good view of Apollo 11. I think, here they come, on the left side, two of them. One object brighter than the other. See the two of them, one above the other? Brightest one, lowest. One's the command module, one's the service module. They each weigh 6 tons. They're just picking up heat now. The bottom one's leaving an incandescent trail. Do you see it flashing? That's a trail of epoxy ablative resin coating. See it brightening up? What a spectacle. It's passing a beam us now at nearly 300 miles. There it goes.
The Apollo 11 with astronauts Neil Armstrong, Edwin Aldrin, and Michael Collins has splashed down in the Pacific Ocean. The historic voyage to the moon and back ended at 11:50 a.m. Central Daylight Time. The landing took place at a point about 900 miles southwest of Hawaii. As the spacecraft re-entered the atmosphere, one of the recovery planes sighted the spacecraft glowing in the early morning sky. Shortly before splashdown, another of the instrumented aircraft spotted Apollo 11. Then the spacecraft was spotted briefly behind the clouds by those on the recovery ship Hornet. At 11:45, the Apollo 11 crew reported that the chutes had deployed. At 11:48, the Hornet reported visual sighting. Then the Apollo 11 itself reported.
Apollo 11, this is Hornet, over.
Apollo Hornet, this is Apollo 11, reading loud and clear. Our position 1330, 6915.
Helicopters immediately began to hover over the Apollo 11, and then the swimmers dropped into the water for the recovery.
Hornet, Goddard voice via ATS.
So Hornet, go ahead.
Roger, you're loud and clear. How do you read me?
Copy you loud and clear.
Roger, we're going to be monitoring this circuit for the recovery sequence. We'll also be extending this circuit onto the White House.
Roger, understand.
White House, Goddard voice.
White House.
Roger, how do you hear me?
You're loud and clear.
Roger, you're loud and clear also. We'll be extending this circuit into the Apollo net at Goddard. Thank you very much.
President Nixon waving to the astronauts. The curtains have been drawn. And there they are in the rear window. President signaling for applause from the crowd. Astronauts gather in the window.
Neil, Buzz, and Mike, I want you to know that I think I'm the luckiest man in the world. And I say this not only because I have the honor to be President of the United States, but particularly because I have the privilege of speaking for so many and welcoming you back to Earth. I can tell you about all the messages we've received in Washington. Over 100 foreign governments, emperors and presidents and prime ministers and kings have sent the most warm messages that we've ever received. They represent over 2 billion people on this earth, all of them who have had the opportunity through television to see what you have done.
All this we pray as our thanksgiving rings out to thee in the name of our Lord. Amen.
Amen.
on Earth, we all know about gravity. But what you might not realize is that depending on where you are on the planet, the strength of gravity is different. For example, up here on a mountain with all this mass under me, gravity is stronger. Water also has mass. And the Earth has a whole lot of water, it's moving around, it's changing phases. If you can track the change in gravity, you can track the change in mass, and that means you're understanding the movement of water. NASA's about to send the GRACE follow-on mission, which will continue to do just that. Let's learn about it on this episode of Crazy Engineering. Okay, everybody, we're here with Neil. He's one of the key engineers on the GRACE follow-on mission. Neil, thank you so much for joining us and answering our questions. Why do we call it GRACE follow-on?
So GRACE stands for Gravity Recovery and Climate Experiment. We're using gravity to track water motion around the planet. And the follow-on is because we've done this before and we're doing it again with 2 new satellites. The original GRACE mission was launched in 2002. They lasted for 15 years and provided amazing science for the scientists.
Both of these missions have 2 satellites. Can you explain to us why we need 2 satellites instead of just 1?
So we need 2 satellites because we're trying to measure very precise small amounts of gravity changes in the Earth. The Earth is actually lumpy when it comes to gravity. Far away from Earth, gravity is just a single number, but as you get closer to the Earth, the gravity changes because the Himalayas have a little bit more mass, certain areas have less mass. And so as a satellite is orbiting the planet, as it comes towards a large mass, like the mountains, it actually will speed up. And then as it leaves, it will slow down. And so with two satellites, we're able to measure the distance between the two.
How far apart are these satellites, and just how precise do they have to have the knowledge of each other's position?
We have the satellites at 200 kilometers apart, but we're measuring down to an accuracy of a micron level, which is about 1/10 of a human hair.
That is extremely precise, but sounds like a very hard engineering problem. What's the technology that lets us do this?
We're using microwave technologies at about 30 gigahertz. Here you see one of the satellites, and 200 kilometers away is the other satellite. And what we're doing is we're firing an RF signal to the other satellite, and the other satellite's measuring that. And as you move backwards and forwards relative to the sine wave, you can measure the distance changes to the levels we need.
Neil, it's been well more than a decade since the original GRACE mission. I assume we're upgrading some of these technologies. Can you describe some of those?
Sure. Like technology advances in general, we've upgraded computer systems, we have more efficient solar cells, we have better star cameras, and like everything else in the future, we now have lasers.
Lasers, yes. What do lasers actually get for us?
So we're actually using the lasers to do the measurement between the two satellites. We're using RF systems from the previous missions. On top of that, we have this new technology demonstrator where we're going to fire laser beams between each other to make a more accurate measurement between the two satellites.
Neil, this is without a doubt one of the coolest missions we've seen. Thank you so much for answering our questions. When can we hope to see this launch?
So we're hoping to hitch a ride with SpaceX rocket later this year, and we should be collecting science data shortly after that.
All right, well, we'll certainly check that out. And everyone out there, check back soon for some more crazy engineering.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything we can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Most early inventors thought that flight control can be achieved by a pilot simply shifting his weight back and forth. The Wrights, on the other hand, knew that controlling the plane would be the key to successful flight.
Release brakes, throttle to afterburner. Watch exhaust temperature. Watch nozzle position. Check engine pressure ratio now. And all this time, steer down the runway. First nose wheel steer, then rudder. Lift nose wheel at just the proper speed to fly off in the least ground roll.
Today, man copes with a highly complex environment with physical abilities no better than he has ever had.
Greater demands on the air crew call for ever closer relationships between man and machine.
Until now, all flyers have used the force of their muscles, multiplied by gears and motors, to adjust wing and tail surfaces.
Your landing gear and flaps are operated hydraulically.
It's about 45 pounds of force to get that stick to move. It's a very athletic endeavor.
An advanced flight control system called the Digital Fly-by-Wire System has been installed by the Flight Research Center in a modified F-8 jet aircraft.
The pilot of this experimental aircraft need only indicate the desired flight path to a computer, which then calculates and actually executes the control changes needed to stay on course.
The heart of the control system is a digital computer and an inertial measuring unit that were developed for the flight control system of the Apollo lunar module. Use of this kind of control system could make air travel of the future smoother and safer by reducing aircraft vibrations caused by turbulent air through automatic response from the computer to the aircraft controls.
We used an F-111 for integrated engine control.
Further mechanization hopes to make more optimum blending of airframe and propulsion system controls.
A computer-controlled flight system, along with some new control surfaces, allow this modified F-16 to maneuver laterally, change altitude without pointing its nose, and perform other unconventional maneuvers.
The Deke system is full authority digital electronic control. The fastest calculation loop in the control is 24 milliseconds.
At Dryden, we had been working integrated controls here over a number of years, so we decided to see if we could extend our integrated control approach to let the engines do all of the flight control.
When Gordon Fullerton lands an F-15 and he hasn't touched the control surfaces, all the people who said it was impossible suddenly don't have a lot to say anymore.
This will be invaluable on military and commercial aircraft of the future.
You can bring it in not for just a survivable crash landing, but a precise normal landing, which is what we did, with absolutely no motion of any external flight controls, purely by modulation of the engine thrust.
Using neural networks to identify aircraft stability parameters and to optimize control performance during test flights will reduce development and program costs.
A neural network is a computer program comprised of a series of examples, and in our particular case, these examples are previous flight data.
Power-by-wire actuators only draw power when the aircraft is maneuvering, so that saves a great deal of energy, which in aircraft translates to fuel.
This new software allowed the aircraft's flight control computer to minimize drag by automatically determining the best setting for thrust vectoring nozzles and aerodynamic controls. Thrust vectoring is the ability to direct an aircraft's thrust for directional control, rather than relying on conventional control surfaces alone. The Intelligent Flight Control experiment, to be tested in early 1999, seeks to enable aircraft control systems to adapt to unforeseen changes in aircraft operating conditions.
In addition to advanced controls research, the FAST system allows for simulating system failures.
Data from NASA's Integrated Resilient Aircraft Controls, or IRAC project, will be used to design and develop aviation systems better enabled to safely fly and land damaged aircraft.
One promising technology that may make it possible to improve both aircraft safety and performance is active stabilization of flutter using advanced flight control systems.
NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello and a very pleasant good evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the final Von Karman Talk of 2022. From Star Trek to Kurt Vonnegut and all the sci-fi in between, people have dreamed of planets beyond our home, beyond our system. In the past 30 some odd years, these dreams have become more of a reality with the field of exoplanet discovery. In this scheme, the nearest known exoplanet orbits Proxima Centauri, the next star over from Earth, and it's a little more than 4 light years away, or 24 trillion miles. If an airline offered a flight there by jet, it would take you 5 million years to get there. However, exoplanets offer a unique view of our solar system and of our home planet. Now, I'd like to introduce our questions co-host for tonight, a public outreach specialist here at JPL, Dr. Nora Bailey.
Thanks, Brian, and hello, everyone. Remember, this is your space program, and we really want you to be involved with this conversation. So if you're watching on YouTube or Facebook Live or LinkedIn, you can go ahead and submit any questions into the chat box right there, and our social media team will bring in as many as possible as we can into our talk tonight. If you don't see the chat box, go ahead and reload the page, and it should be right there.
Thank you, Nora. Now, our speaker tonight is a technologist for the Nancy Grace Roman Space Telescope, CGI. She received her PhD in astrophysics from the Université Joseph Fourier in France, was awarded JWST time through several GO programs, including one as a PI. And when she's not working, you can find her exploring national parks from Yellowstone to Mauna Loa or to the Everglades. Please welcome Dr. Marie Igouff. Hello.
Hello, Brian.
How are you today?
Very good. Very pleased to be here.
Well, it's wonderful to have you here. Let's just dive in. Let's start with the main topic. What are exoplanets? What are we talking about tonight?
Yeah. So exoplanets are planets that are located outside of our solar system. Those distant worlds are extremely diverse, and although some may look very similar to the planets of our solar system, we know for sure that some of them are actually pretty different. So let's have a look at the first slide, please. Yeah, so as a reminder, we have two types of planets in our solar system. On one side, we have the small rocky planets that are also the closest to the sun. They're called Mercury, Venus, the Earth, and Mars. And on the other side, we have the gaseous giant planets that are also the furthest from the sun. They're called Jupiter, Saturn, Neptune, and Uranus. And before discovering the presence of exoplanets, the solar system was the only model of planetary system we could think of. And it was very hard to think about other models of exoplanetary systems.
So with that, of thinking of ideas of different models and different systems, how are these exoplanets teaching us about our solar system?
Yeah, so one thing we learned by studying exoplanets is the existence of planets that are dramatically different from the planets of our solar system. So on slide 2, we can see it. So the first planet discovered around a solar-type star in 1995 by Nobel Prizes Michael Mayer and Didier Queloz was a pretty different kind of object. It's a gaseous planet, much larger than the Earth and situated much closer to its star. And it only takes 4 days to complete its orbit around its star. And as a comparison, Mercury, which is the closest planet in our solar system, orbits the sun in 88 days. So this type of planet is definitely not something we can see in our solar system. Could you bring also slide 3, please? And so since that discovery, we found many other exotic planets that don't have equivalent in our solar system, such as an entire new category of planets of size between the size of the Earth and the size of Neptune, that we call either super Earth or mini Neptunes. We also have lava worlds, puffy planets that have the density of styrofoam, and also dense core of planets that are still orbiting their stars, but without any atmosphere. We also have planets orbiting groups of stars, also orbiting dead stars, and even rogue planet that doesn't even orbit around the star. We have highly eccentric planets, and in fact, many of the exoplanets discovered so far have a higher orbital eccentricity than the planet in our solar system. So studying those exoplanets teaches us a lot about our own solar system. For example, it is very possible that we had a super Earth in the past that would have been expelled from from the solar system, or also collided with a gas giant. It's even possible that it's still here somewhere and we haven't found it yet.
Well, you talk about all these different types of planets that we kind of don't even think of in our solar system. How many planets have we discovered?
Yeah, so can you bring the slide 4, please? So as the 1st of November, there were more than 5,000 confirmed exoplanets and more than 9,000 candidates needed to be confirmed. And one telescope that revolutionized exoplanet detections was Kepler, the Kepler Space Telescope that was launched in 2009. And one of Kepler's findings is that there is at least one planet on average per star. And as a matter of perspective, our galaxy, the Milky Way that you can see on this picture, has a couple of hundreds of billions of stars. So that means that we discovered only a tiny, tiny fraction of exoplanets in our galaxy. So there is quite a lot of room for incredible discoveries out there in the field of exoplanets. So to diving a little bit more, let's have a look at the slide 5, the discovery timeline of those exoplanets. So this figure shows the number of detected planets as a function of time. And we can see that this number is increasing as an exponential speed. The first discovered planet was in the 1990s. And as you can see, this is a pretty young field. I mean, it's less than 30 years. And exoplanet discovery is almost routine now, we can say that. And because those years, we discovered one planet every 2 days in average. So, of course, this was not linear because we started with a pretty small discovery rate, and then the dedicated missions were built to detect those planets. And with every new mission, the yield of planets grew larger and larger.
So if that yield's growing larger and larger, we're finding them exponentially. How do you find them? How do we discover these planets out there?
Yeah, so another thing that we can see on that figure is that the majority of detected planets have been discovered using two main techniques, the radial velocity technique and the transit technique. So we'll see what are those techniques. So first illustration 6 will show a little movie of the radial velocity technique. So with that technique, we detect the tiny movement perturbation an exoplanet has on its star. That slight movement affects the star's normal light spectrum or color signature. And the spectrum of the star that is moving toward us appears slightly shifted toward bluer and shorter wavelength, while when the star is moving away, its spectrum is shifted toward redder and longer wavelengths. So that's for the radial velocity method. And in the next movie, we'll see the transit technique, how it works. And so with that technique, we measure how the luminosity of a star evolves over time. So most of the time, that luminosity is constant and quite boring. But some variable star, we will see in those variable stars that this luminosity can vary in a random fashion because of the activity of the star itself. But in some very rare occasion, we can see periodic decreases of the luminosity of that star, which indicates that one or several planets are passing in front of the star. So those techniques are what we call indirect technique, because exoplanets are detected through the indirect effect they have on their host star, but we don't actually see the planet themselves.
Well, if you're calling these indirect techniques, if we flip the coin, do we have direct techniques? Are there more direct ways to find these planets?
Yeah, I'm sure you're gonna ask that. So yeah, Alpha, this is pretty challenging, as you can imagine, but we'll see that. There's another technique some astronomers and myself in particular interested in. This technique is called direct imaging, or also called high contrast imaging. Okay. And so what is interesting with this technique is that we can actually get picture of those worlds. And this is a game-changing technique because, first of all, the type of exoplanet that we can detect with this technique is very different from the exoplanet we can detect with other indirect techniques. The second thing is that we can know exactly where the planet is and learn about the orbits of those planets. And finally, we can directly probe the chemical component of that atmosphere at different wavelengths and learn crucial information on those planets, such as their mass, their gravity, and whether certain chemical components are present in their atmosphere. So let's pull out illustration 8. Now we have only a few pictures of those exoplanets so far. And the reason is that it is pretty challenging. See, because the star is so bright that we first need to block its light to be able to see the light of the faint planet. And we're doing that by using a very small optical component that is called a chronograph that acts similarly to what the moon does to the sun during a solar eclipse. So we can see on illustration 9 a picture of such a solar eclipse. And if you are lucky enough to have experienced a solar eclipse, I really recommend that if you have the chance one day. You may have noticed that we can see stars in the middle of the day. And with a chronograph, we can do the same with any star and hunt for planets that orbit around them. But the extreme contrast of flux between the planet and its star is not the only challenge we're facing. We also need enough resolving power to be able to separate angularly the planet from the star in the image formed by the telescope. And for that, it really helps to have a big size telescope. And it also helps to observe stars that not too far from us, which limit a little bit the number of targets that we can observe with that technique. And one of the other challenge of direct imaging is that we need telescopes that are sensitive enough to detect a very faint signal from the planet. And here again, telescopes with big mirrors help for that. And also telescopes that are in space are sometimes more sensitive than telescopes on the ground, depending on whether we are observing in the infrared, the visible, or other wavelengths.
So you're talking about these different wavelengths, you're talking about these, I mean, it sounds like there are a lot of challenges in order to try to discover anything out there.
Yeah, there are definitely a lot of challenges. So let's have a look at the illustration 10. I would like to show you a video that illustrates how we solve the contrast issue with a chronograph. I think it's a very, very nice video. So you'll see here an exoplanetary system orbiting a star, and you want to observe that system with a telescope. So the light is going to go through the telescope, and we're going to see what's happening inside the telescope. So here, the light is going to first reach a mirror and then a couple of optics and create the image of the star on the detector. And then you have a chronograph that you put in there to remove most of the starlight. So that's one component of the chronograph, a second component of the chronograph, and you see that the light disappears. And then you can ask, but it will hide also the planet, but that's not the case because the planet is off axis and is not hidden by the chronograph. It's not blocked by the chronograph. So there are two planets in there, but we cannot see them because there are a lot of residual, instrumental aberrations in the instrument that prevent the chronograph to work optimally. So we want to correct in real time those instrumental aberrations with a deformable mirror to be able to further remove the residual speckle or residual starlight that we can see on the image. And it's often not sufficient because we also need to use and develop state-of-the-art post-processing technique to further remove the starlight. So, I'm pretty sure that now that you have, you know a little bit more about how those chronograph works, you would like to see what it does in reality. I mean, what a real picture of exoplanets. So let's go to the slide 11 that shows an actual movie, not even an image, an actual movie of an orbital, an exoplanetary, an entire exoplanetary system that orbits the star HRT 799. So I think it's a particularly stunning video because you have to imagine, this is a system that is at 130 light years from us. And the HRT 799 star hosts not less than 4 giant planets that are about 10 times more massive than Jupiter and approximately the same diameter as Jupiter. And as you can see, we're pretty far from the artist's concept illustration that we're seeing all the time on the internet for exoplanets. We currently don't have the capability to take such pictures, but what you have in front of you is what we can do currently, and I think it's still pretty amazing in my opinion.
It is pretty amazing. I could watch this all day as they orbit around. You talked about the star called HR 8799. Really rolls off the tongue there. How do some of these exoplanets get their names?
Yeah, so exoplanets can actually have several names. Okay. So the most conventional way, or at least the way astronomers call an exoplanet usually, is by using the name of the star plus some minor case letters. But planets are sometimes called by the mission that discovered them. That's the case, for example, of the CORE mission, the Kepler mission, or the TRAPPIST telescope. And the letters, they are usually given by alphabetical order in the order of the planet discoveries. So let's take the example of the TRAPPIST-1 system on illustration 13. Yeah, it's not the good one. Sorry, 13 should be, yeah, okay. Yeah, there's any issue with the numbering anyway. So if we go back to the movie of the HRT 799 exoplanetary system that we were showing just before, yeah, exactly this one. So if we take the example of this movie, the planet that is the furthest of the star is called HRT 799b. And then after, the one that is a little bit closer is called HRT 799c. And then we have HRT 799d and HRT 799e. And the reason for that is that the planet that is further from the star is the one that is the easiest to spot in direct imaging, because the better we get at developing post-processing technique, the better we are, and we can remove the residual starlight and be able to detect the planets that are closer to the star. But for example, if we take the example of the TRAPPIST-1 system, which is the one that we saw just after, I think.
13 or 14?
No, not even. Should be 14 on my, yeah, great, thank you. So this famous exoplanetary system was discovered with the ground-based TRAPPIST telescope using the transit technique. And the first discovered planet was planet B, which is the one that is closest to its star. So it's different from what we saw just previously. And then comes C, D, E, F, G, and H that were successively discovered. And the reason why the first planet to be discovered in the system are the closest is that they were discovered using the transit technique, as I said, for which it is actually easier to detect the planets that are closest and more difficult to detect the further planets. Okay. So, yeah, let's see. I think we can switch to the next illustration then. Yeah, which is this one. Awesome. So one thing I wanted to mention, which is a cool thing, is that the International Astronomical Union make possible to the general public from the entire world to choose the name of a subset of exoplanets. And there were a couple of runs in 2015 and 2019. And the latest round to name exoplanets is still going on at the moment. So if one of your dreams has always been to name an exoplanet, I will really suggest to go for it and check the website, the Name ExoWorld website that should you should see on your screen. Sorry, and check that website.
I've always wanted to name a planet. There's all sorts of things I wanted to name. So I'm going to go take a look at that after this. So that's what's down the road for me. But what's next down the road for exoplanet and exoplanet discovery?
Yeah, so next slide is should be a nice summary of the major exoplanet missions. So the past, current, and future missions. And if you look at the top right, you will see a space telescope that has been recently launched and commissioned, the James Webb Space Telescope, or JWST. And after JWST, the next down the road will be the Nancy Grace Roman Space Telescope, a Hubble-sized telescope that will be launched in 2026, and that will cover some great exoplanet topics. So let's dive a bit more with what's coming in the next 10 years. So next slide. How not to mention the first exoplanet imaged with James Webb. And this has been recently imaged, right, that there are image as of the planet HAP 65426b that was released about 2 months ago. So this planet is a 9 Jupiter a 9 Jupiter mass planet that is at 385 light years from Earth. And it was discovered in 2017 with the SPHERE instrument on the VLT. And this planet was chosen to be a prime target for James Webb because it is at wide separation of its star, and that's pretty easy to spot with JWST. But we expect JWST will discover new exoplanets by dozen pretty soon. And for example, in the next slide, we can see an example of target that we will observe with James Webb, and you can recognize the HRT 799 system that we talked about earlier. So we will observe that target very soon with James Webb, and we will not only further characterize the exoplanet, the 4 exoplanets that are in that system with those observations, but we also will look for new planets in this system. And there will be also many other systems that will be observed as well. So we don't expect James Webb to find thousands of exoplanets like previous missions such as Kepler or TESS, because this telescope is not dedicated to exoplanet science. JWST is going to do a lot of other great science besides exoplanets, even if maybe we can expect that 25% of JWST time may be on exoplanet science. But we expect great discoveries in the field of exoplanet characterization, like illustration. The next illustration is going to show. So, okay, it's sorry, it's not this one. It should be the spectrum of James Webb.
I think that's number 19.
Yep. Excellent. Thank you. So this illustration, this figure shows the spectrum of an exoplanet, which is called WASP 96b, which is a hot gas giant exoplanet. And it has half the size of Jupiter, and it orbits its star every 3.4 days. And it's located at 1,150 light years from us. And JWST was actually able to detect water in the atmosphere of this planet, which was apparently quite unexpected for that particular object because it was previously thought to be cloudless, completely cloudless. So it was quite a surprise. And JWST will probe the atmosphere composition of many known planets to identify chemical components such as water, methane, or carbon dioxide. And it's going to do that with a lot of known exoplanets. And it really opened the path to statistical analysis of those exoplanets. And so with this capability, we hope to learn more about the composition of exoplanet atmospheres and then how they were formed, and also learn more about the planet in our own solar system as well.
James Webb is kind of, it's astounding, and the images and everything we find from that. But I want to talk about what you're going to be working on, the Nancy Grace Roman Space Telescope. Can you tell us more about that with this field?
Yes, of course. So yeah, next slide should be the Roman Space Telescope slide. Yep, awesome. So Roman is the next big NASA mission to be launched in 2026 with two different instruments. So first we have a science instrument, which is called a wide field imager, that will detect thousands of new exoplanets using the techniques of transit and microlensing. And second, we will have a technology demonstrator, the chronograph instrument, that will demonstrate the key technologies that we need to image terrestrial planets in the habitable zone of their star and characterize their spectra. So you can see, for example, one image, simulated image of what we could see. You might think, okay, it's not. It doesn't seem better than what we saw already, but there is actually a big difference. Is the contrast that we were able to reach with Roman is several order of magnitudes the contrast that we are able to reach right now with the current instruments. So with the current instrument, we can do contrast of 10 to the minus 6, for example. But here we're going to be with Roman, we're going to be able to observe planets with contrast to 10 to the minus 9. And that's all this while demonstrating the technologies that we will use to to detect terrestrial planets using direct imaging in the future. So the next slide will show that this Roman telescope will open the path to the next generation of space-based telescope that will look for signs of life on exoplanets. But for those telescopes to become reality, there's still a lot of work to go, and we'll have to be patient and wait at least 20 years or more.
That's amazing, and it's astounding, and I'm looking forward to everything that you find with that telescope. The audience have been asking amazing questions tonight, so I'm going to throw it over to Nora, and let's get these audience questions in our talk tonight.
Yeah, thanks, Brian. This was a great talk, and there have been so many awesome questions from our audience. So Cyclops on Twitter asked, is there anything in the works to send a spacecraft to any of these exoplanets?
Yeah, I've heard about some projects that could visit some of the planets that are the closest to us. So the planets in the Proxima Centauri system. Which is the star, which is our neighbor, basically, the star that is closest to us. However, it's a star that is located at 3 to 4 light year. So that means that if we were to go to that star at the speed of light, it will take us 3 to 4 years to go there, but we are pretty far to go at that speed. And so it's for now a little bit out of reach. But there are definitely some projects, and people are thinking about that because it's like a fun thing to think about visiting another exoplanet.
Yeah, Donnie on LinkedIn actually asked, would we ever send humans, not just spacecraft? Do you think if we had the advanced technology, would we be able to send humans there as well?
Yeah, so same kind of the same answer here is that we don't have the technology for now to even send a spacecraft. So I'm pretty sure if we had the technology to go, some people would like to go. But yeah, it's definitely it's already a challenge to go to Mars, right? Or even to go back to the moon. So yeah, it's definitely not the same distance. So yeah, it's not for tomorrow. And then people in our generation are probably not gonna see that in our lifetime.
Yeah, it'd be a long trip. So Vector on YouTube asked about the TRAPPIST-1 system that you were talking about. Is it possible that there are planets that are either really small or on tilted orbits that exist in that system and we just don't know about them because they haven't transited?
Yeah, it's totally possible. I mean, anything can be possible. It's possible that there are some, gravitational interaction in the system between some planets that makes a planet change orbits and have an inclined orbit. That would be possible. But we don't know, and that's one of the advantage to use several techniques to observe the same system because they are complementary, right? So if we don't detect with the transit because they are not in the same same plane as the other planets, we could, for example, detect another planet in that system using the radial velocity technique, or even direct imaging if we're lucky. But the TRAPPIST system is a little bit far to be accessible for direct imaging, but who knows, someday. Yeah.
Awesome. Zaker on LinkedIn as well as Cyclops on Twitter both asked about how we actually identify the chemical composition of these exoplanets, like you were showing with the JWST spectra.
Yeah, that's a great question. So to do that, we have two techniques. So the first one is to observe the same system using different filters at different wavelengths. So that gives us some clues about the composition of those planets. So that's something that we're going to do on James Webb. Using, for example, the NIRCam or the MIRI chronograph that we have on James Webb. But we don't have the capability to do a spectrum using direct imaging because we don't have a prism on the instrument that have the chronograph. We have some spectrograph, which are kind of prism, elaborated prism on instruments that we are using to disperse the light that we receive from a planet or a star to create those spectrums. So this is how we create those spectrums. So here, as you can see on the top right, the spectrum has been done using the NIRISS instrument on James Webb. And this has been done using the transit technique in particular. On Roman, it's going to be a little bit different, is that we're going to combine a chronograph and a spectrograph so that we will be able to not only do some direct imaging and see pictures of those planets, but also we will have the capability to take those pictures and put them in a spectrograph and also extract the spectrum from that star. So this is why this technology demonstration is so important, because combining the chronograph and the spectrograph will give us the capability to really observe and characterize the atmosphere of those planets.
Thanks. That's really exciting. Really looking forward to Roman. So Tom on LinkedIn asked if there's any kind of special exoplanet science that can actually be done taking advantage of being at the Lagrange points, such as L1.
Oh, L1 or L2 maybe, or whenever. Yeah, I mean, all exoplanet science can take advantage of being at that point, because those kind of points are gravitationally stable point in space that offer much stable condition for observation. And so when we observe exoplanets with any kind of technique, basically, the more stable a telescope is, the better, right? So that's one thing. And if we want to increase the detection capabilities, we want to spend more and more time on those planets. So we want to be as stable as possible, because you're going to stay for a long time on those planets. And the second great advantage of going to L2, for example, such as JWST is at L2, Roman will be at L2 as well, is that we the telescope is going to be further from the Earth, and the Earth is a kind of black body that's going to emit a lot of infrared light, and this is also, for example, the wavelength in which James Webb observes, right? And so you don't want to, I mean, the Earth is pretty bright for James Webb because it's observing in the same wavelength that the Earth is emitting. So the further you are from the Earth, and the better it is for exoplanet science, in particular for James Webb.
Awesome. So Sarenga on LinkedIn asked, out of all of the exoplanets discovered so far, how many closely resemble Earth in terms of atmosphere and land, or even water?
Yeah, there are a couple of parameters, I mean, ingredients, we'd say that we are looking into. And so first, you need to have a terrestrial planet, a rocky planet, to be close or similar to the Earth. So that's one thing. The second thing is you have to have an atmosphere. And the third thing is that if we want to find something similar to the Earth, we want to find a planet that is located in the habitable zone of its star. So that means that this is a zone where water can exist in liquid form, and that could be some very conditions for the life to develop in such a planet. So for now, we know that there are some terrestrial planets that exist in the habitable zone of their stars, but we still don't know if those particular planets, and there are a couple of them, there are not many, but there are a couple of them, we know about a couple of them, and we don't know yet if those particular planets have an atmosphere still. And so that's one of the questions that James Webb will have to answer, actually, by pointing some of the planets that are in the TRAPPIST-1 system that are pretty good candidates for that. So we'll learn more with James Webb.
That's really exciting. It's one thing I love about exoplanet science is there's just so much left to learn. So we just have time for one last question. I think this will be a great one to end on. This is from Anaya on YouTube. And she asked, how did you know you wanted to study this topic, and what tips would you have for a younger person or anyone who's interested in astronomy and astrophysics?
Yeah, that's a great one. So I always been obsessed kind of by astronomy. When I was like super young, I was always looking for the moon, and so I kind of knew, I mean, that I liked it, but I didn't know that it could be like a job, right? And so I discovered that when I was a teen, reading a science magazine, and I discovered that you could actually be an astronomer and study this as a job. And that day I figured out that that's what I wanted to do, right? And I didn't know that I would wanted to work on exoplanets because at the time we hadn't. I'm that old. At the time, we didn't know that exoplanet existed. And so I was lucky to be here. I mean, to be around when and pretty. I mean, that young when we discovered the first exoplanet, and so I followed all that stuff. And I had the opportunity when I was a student to do an internship at the Observatoire de Paris, so it was in France, and this internship was in exoplanets. And since that day, I knew that I wanted to be an astronomer. I didn't know what kind of astronomer I wanted to be. But that day I said, okay, exoplanet is so cool. I just want to to be part of it. And to answer the second question about is there any tips, I'd say one of maybe the best tip I would give is that if you know you want to do something and you're really passionate about it, and it's part of you kind of, you should really persevere because it's very hard. There are a lot of obstacles, and it's only by persevering that you can reach those goals and be able to do what you want to do.
That is a perfect way to end tonight. Unfortunately, everyone, that is all the time we have for this evening. I do want to thank our co-host, Dr. Nora Bailey, and our terrific speaker, Dr. Marie Igou, for their joy and their expertise. We also want to thank Christopher, Colin, Max, Bill, Gabby, Mark, Curtis, Nikki, Joey, and everyone that you don't see, but they're there monthly behind the scenes who make these public talks possible. Our final thank you is to you, the audience, who join us every single month. This is your space program, and we're grateful you invite us into your lives every month with these Von Karman talks. Our next talk will be in January of 2023. Thank you again to our speakers. Stay safe, stay kind, stay curious, and we'll see you next year.
I got rice cooking in the microwave. Got a 3-day beard I don't plan to shave. And it's a goofy thing, but I just gotta say, hey, I'm a-doing alright. Yeah, I think I'll make me some homemade soup. I'm feeling pretty good, and that's the truth. It's neither drink nor drug induced. No, I'm just doing alright. And it's a great day to be alive. I know the sun's still shining when I close my eyes. There's some hard times in the neighborhood, but why can't every day be just this good? Oh, yeah. It's been 15 years since I left home. Said good luck to every seed I'd sown. Gave it my best and then I left it alone. I hope they're doing alright. Now I look in the mirror and what do I see? A lone wolf there staring back at me. Long in the tooth but harmless as can be. Lord, I guess he's doing alright. And it's a great day to be alive. I know the sun's still shining when I close my eyes. There's some hard times in the neighborhood, but why can't every day be just this good? Sometimes it's lonely, sometimes it's only me and the shadows that fill this room. Sometimes I'm falling, desperately calling, howling at the moon. I had to. Or take my old Harley for a 3-day cruise. Might even grow me a Fu Manchu. And it's a great day to be alive. I know the sun's still shining when I close my eyes. There's some hard times in the neighborhood, but why can't every day be just this good? It's a great day to be alive. I know the sun's still shining when I close my eyes. There's some hard times in the neighborhood, but why can't every day be just this good?
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Mission Specialist.
I'm Jeremy Hansen. I'm a Mission Specialist.
I'm Victor Glover. I'm the pilot.
I'm Reed Wiseman. I'm the commander for the Artemis II mission to the moon.
To the moon.
To the moon.
To the moon.
When I was young, I had a poster of the Earthrise picture, the famous picture that was taken on Apollo 8. And the fact that it was a human behind the lens that made that picture so profound and changed how we all thought of our own home was so amazing to me. The moon is not just a symbol of thinking about our place in the universe. It's not just a symbol of exploration. It's actually a beacon for science. It's a beacon for understanding where we came from.
You know, pushing ourselves to explore is just core to who we are. That's a part of being a human. That's our nature. We go out there and we explore to learn about where we are, why we are, understanding the big questions about our place in the universe. The exploration we're doing is the first few steps on the path of getting humans to Mars.
The Artemis campaign of missions have set such an ambitious goal for humanity that it's inspiring contributions from around the globe. Not just one nation is inspired and moved by this, but nations from around the globe are coming together.
When I look at the Artemis II crew with Victor, Christina, and Jeremy, they want to go do this mission. They are keenly driven. They are humble to a fault. It is so cool to be around them. Artemis II is a huge mission, but I hope we will look back and realize that this was one tiny step in humans on Mars and a sustained presence on our moon.
Force stage engine start.
Artemis II will be NASA's first crewed flight test of the Space Launch System rocket
and Orion spacecraft around the moon.
To verify today's capabilities for humans to explore deep space
and pave the way for NASA's long-term human and scientific presence
on the lunar surface.
We are ready.
We are going
to the moon
for all humanity.
We are Artemis.
On September 11th, NASA astronaut Frank Rubio completed his 355th day on board the International Space Station, surpassing the record for the longest single spaceflight by a U.S. astronaut, which was previously held by NASA's Mark Vande Hei.
Frank, you've made all kind of records.
Agency leadership congratulated Rubio on the accomplishment during a call to the station. By the time Rubio returns home on September 27th, he will have spent about 371 days in space. The crew of our SpaceX Crew 6 mission is back home after spending about 6 months on the space station. On September 12th, a few crew members, including NASA astronauts Steve Bowen and Woody Hoberg, talked about the mission during a news conference at our Johnson Space Center. The highlights of the flight included Bowen's U.S. record-tying 10th career spacewalk. Our OSIRIS-REx spacecraft recently made a course adjustment to better position itself to release a capsule carrying sample material from asteroid Bennu toward the designated landing zone in the Utah desert. The capsule is scheduled to make a parachute-assisted landing on September 24th. OSIRIS-REx is the first U.S. mission to collect a sample from an asteroid. According to our Goddard Institute of Space Studies, the summer of 2023 was our planet's hottest summer since global records began in 1880. June through August was a combined 0.41 degrees Fahrenheit warmer than any other summer in NASA's record. This new record comes as exceptional heat has swept across much of the world, exacerbating deadly wildfires, resulting in searing heat waves, and likely contributing to severe weather. For more details, visit nasa.gov/Earth. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/Twan.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
For generations, we have dreamed about a place to live and work in space, a space station. And right now, 260 miles above us, that dream is a reality. We dreamed that life up there would benefit life down here. That dream has come true. Can research on board the space station lead to cleaner drinking water on Earth? Can it help farmers produce better crops? Can it inspire a generation of students? Can it even save a life? The answer to these questions is yes. It already has. As the work aboard the International Space Station begins to reach its potential, the benefits to humanity are evident. These are just a few of the stories from people who have realized those benefits in their own words.
Is that 2? You say 2?
I found a big lump in the side of my face, and I kept going to doctor after doctor. And I was in so much pain at that time. I was like dying in bed. It hurt so bad. I've never been in so much pain. I went for my first MRI and then it showed up with like hundreds of tumors all over. And then they sent me to, not Dr. Sutherland, but someone who works in his office. And he thought it was neurofibromatosis, which I have.
We didn't even realize what that was. We'd always heard it called the elephant man disease. There's different types of neurofibromatosis. One of them, the tumors grow on the outside of your skin. The other one, the tumors grow on the inside, and hers grow on the inside.
A long time ago, when we were thinking about this, we approached McDonald Detweiler Associates. It's a company that happens to be located in Canada that built robots for space. They built what Canadians call Canadarm, and then they constructed the special purpose dexterous manipulator for the International Space Station. And the idea was, if they could build such complex robots, perhaps in collaboration with medicine, we could build a robot that could operate inside an MRI machine.
We did not realize that it was built out of the same material as the space arm, and we're quite amazed that that's what he had made it out of.
But it's the multi-dexterity of the robot, and that robot could perform tasks that made us become increasingly confident that we could overcome the challenges related to building a robot that could operate inside an MR machine with the precision, the accuracy, and the dexterity of a neurosurgeon. It just so happened that the first individual was a young woman, and the young woman harbored a fairly complex tumor underneath the front part of her brain. A machine like NeuroArm can manipulate tools at an accuracy of 50 microns. That is overwhelmingly superior to what the best surgeon might be able to do.
I think it's fabulous. To me, it's actually mind-boggling that someone can take that material and put it into a life-saving device that can help millions of people.
I honestly think that right now I'd be bedridden. I would not be able to get out of bed if it was not for my doctors. My parents would be taking care of my kid right now. I guess I'm glad that it hopefully helped people who have my disease, and I hope that it helps people who need surgery in the future. If they're ever propositioned with a chance in the future to have something done like this, I hope they take it.
Estamos en la comunidad Tres Picos.
We're in the town of Tres Picos.
Es una purificadora de agua que utiliza.
This is a water purifier that uses technology developed by NASA and makes free purified water available to all of the people of the community.
La tecnología fue desarrollada para
the technology was developed by NASA for the International Space Station.
En el caso de esta comunidad, viene de la red pública.
In this community, the water comes from the town. But in other communities, where we are working in Chiapas, it comes from the wells, from rivers, from streams, from springs. The water can come from practically any source that you can imagine. People who drink contaminated water alter their health. Their children's development is diminished.
Yo me llamo Raquel Pérez Pérez y soy asistente.
My name is Raquel Pérez Pérez, and I am the campus assistant of this school. There were lots of children with parasites and stomach bugs before the purified water came. Now the kids are healthier because they now drink purified water from the plant. The energy that is being used is solar. And the children come to recess with their cups and they get the water themselves. They are happy now and they want to come and drink water all the time.
When you get involved with a plant of this kind that gives people access to pure water for human consumption, that is going to prevent people from getting sick. What you're really doing is improving people's health, but also you're improving the economy for these people. If we could put one of these plants in every community and have people use it, it would have resolved one of the most important sources of health problems, at least in the rural areas of Mexico. That's the truth. If it is well used, it can change the lives of an entire community. It gives you children that learn more. It gives you parents who spend less money on medicine. It changes the future.
Our farm is called AWG Farms, started back in 1975. It's a family-run farm. I have two brothers now and my son-in-law is in the operation. This will be a third-generation farm in this particular area. The main crop is sugar beets. Then we have spring wheat, sunflowers, soybeans, corn, and once in a while we'll raise some edible beans. Remote sensing is a way to look at our crops during the growing season to be able to determine if we need to do any monitoring of disease and or fertility differences. There was an organization over in Grand Forks, North Dakota called UMAC. That organization put a camera on the space station called Isaac. Well, the biggest problem with satellite imagery is the fact that Landsat we get every 16 days. And on that 16th day in this region, if we have cloud cover, that image is virtually useless for us. So then we have to wait another 16 days. The biggest thing with Isaac, we would get much more often. When we wanted to get that particular image, Isaac gave it to us when we wanted it versus a more rotational type satellite. And they were able to get imagery to us with a couple bands of light, the more necessary ones that we needed, which is near infrared and red. Near infrared band is something to do with biomass, how the crop is growing. More biomass, usually more yield potential. We're able to obtain a piece of software that's written by a local programmer in this region that allows us to take these images and manipulate them into zones within the field itself. And by doing that, we can see different patterns in the field. And within those patterns, we can manage the field differently based off of biomass or reflectance of the field itself. It's just a tool that we can use it as a reference to be able to make better decisions. And by doing that, our farm is more profitable. And that to me is very important.
I grew up out in the country in Indiana. Corn and soybeans were the main crops. I had always been interested in technology and in science. Being out in the rural setting, there wasn't a whole lot of support for this. Space Jam is an annual weekend Boy Scout event, and we do all kinds of technology-based things. We have about 1,000 people that come every year. This is our 7th year doing it, and it's a blast every year. The contact with the International Space Station was one of the driving forces that helped to create Space Jam. In fact, the first Space Jam was really basically only about the contact.
It was a dream of the ham radio operator to say, hey, I want to talk to the astronauts on the space station. How cool could that be? That's the top of the game.
Each year we call up the International Space Station and we give these young kids the opportunity to ask questions to the astronaut.
Is it true that it will take over a year to get to Mars and back over?
It absolutely is true.
The first time that I remember really having this real impression was, I think, the third year we did this. I was in charge of actually calling up the space station and establishing the contact. We were out in the middle of the night in a field, and I said, NA1SS, NA1SS, this is WB9SA, calling for a scheduled contact. Do you copy, over? And I said it again, and all of a sudden, real crisp comes back, WB9SA, this is the International Space Station, and how are you doing tonight? And we're like, oh, this is amazing. I graduated as valedictorian, and I was lucky enough to be admitted to Princeton with a complete scholarship, and I then moved to San Francisco, where I'm a software engineer. So I went from living on a farm to living downtown in San Francisco, writing software for people. It was a really amazing experience to do all that.
Minas Gerais is a large state. Our territory is about the size of France, and we consist of 853 units and municipalities. There are large distances between our communities and many very isolated rural communities. We are using new technology that impacts the quality of prenatal care and the diagnostic capacity of the primary care doctor in these situations involving distant, isolated communities.
Providing medical care for people in remote locations, like distant rural communities or the International Space Station, can be difficult, because trained medical personnel are not always available. NASA research teams develop techniques that enable astronauts aboard the space station with minimal training to operate an ultrasound device using simple printed guides. The ultrasound images are transmitted in real time to a doctor back on Earth, who can make medical decisions without actually being aboard the station. These same techniques have been adapted for use with portable ultrasound devices in communities where expert medical care is not always available.
My name is Joaquim Diniz. I'm a doctor in the town of Manga. In Manga, people live with a particularity, and that is isolation. We have a geographical barrier that is the São Francisco River, which is both a blessing for the region, but it also isolates us. We live in a region where financial resources are few. People do not have a lot of work, but they are honest, good people who do not have much opportunity. So there are many needy people who need these resources and rely only on this institution to provide assistance. This is a technology that helps us solve many problems. That was the case of a patient who came to the hospital with severe respiratory failure, and the people realized she would die in just 20 to 30 minutes. We talked with Dr. Parzelli, who was training us to use the ultrasound. He came and applied the ultrasound and discovered large amounts of fluid around her lungs and heart. We performed the procedure and drained a lot of fluids. In 10 minutes, the woman immediately experienced an improvement, and in half an hour was already walking. It was like a miracle, a rise and walk. She was dying in front of us without people knowing what was happening. This ultrasound was instrumental in saving the life of that patient.
We've only begun to see the International Space Station's benefits to humanity. These are just a few of the ways that the science and research conducted aboard the ISS is improving lives today. There are countless more benefits to come, sometimes in ways that we have never predicted. Every day, hundreds of scientists around the world are working with the crews on board the International Space Station to perform life-changing research. Every day, they use the weightless environment of space to conduct experiments in ways that can't be done here on Earth. And every day, those experiments improve life for people all over the world. This will be the legacy of the International Space Station's benefits for humanity.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
I'm a mission specialist.
I'm Jeremy Hansen. I'm a mission specialist.
I'm Victor Glover. I'm the pilot.
I'm Reed Wiseman. I'm the commander for the Artemis II mission to the moon.
To the moon.
To the moon.
To the moon.
When I was young, I had a poster of the Earthrise picture, the famous picture that was taken on Apollo 8. And the fact that it was a human behind the lens that made that picture so profound and changed how we all thought of our own home was so amazing to me. The moon is not just a symbol of thinking about our place in the universe. It's not just a symbol of exploration. It's actually a beacon for science. It's a beacon for understanding where we came from.
You know, pushing ourselves to explore is just core to who we are. It's a part of being a human. That's our nature. We go out there and we explore to learn about where we are, why we are, understanding the big questions about our place in the universe. The exploration we're doing is the first few steps on the path of getting humans to Mars.
The Artemis campaign of missions have set such an ambitious goal for humanity that it's inspiring contributions from around the globe. Not just one nation is inspired and moved by this, but nations from around the globe are coming together.
When I look at the Artemis II crew with Victor, Christina, and Jeremy, they want to go do this mission. They are keenly driven. They are humble to a fault. It is so cool to be around them. Artemis II is a huge mission, but I hope we will look back and realize that this was one tiny step in humans on Mars and a sustained presence on our moon.
Before stage engine start.
Artemis II will be NASA's first crewed flight test of the Space Launch System rocket
and Orion spacecraft around the moon.
To verify today's capabilities for humans to explore deep space
and pave the way for NASA's long-term human and scientific presence
on the lunar surface.
We are ready.
We are going
to the moon
for all humanity.
We are Artemis.
On September 11th, NASA astronaut Frank Rubio completed his 355th day on board the International Space Station, surpassing the record for the longest single spaceflight by a U.S. astronaut, which was previously held by NASA's Mark Vande Hei.
Frank, you've made all kind of records.
Agency leadership congratulated Rubio on the accomplishment during a call to the station. By the time Rubio returns home on September 27th, he will have spent about 371 days in space. The crew of our SpaceX Crew 6 mission is back home after spending about 6 months on the space station. On September 12th, a few crew members, including NASA astronauts Steve Bowen and Woody Hoberg, talked about the mission during a news conference at our Johnson Space Center. The highlights of the flight included Bowen's U.S. record-tying 10th career spacewalk. Our OSIRIS-REx spacecraft recently made a course adjustment to better position itself to release a capsule carrying sample material from asteroid Bennu toward the designated landing zone in the Utah desert. The capsule is scheduled to make a parachute-assisted landing on September 24th. OSIRIS-REx is the first U.S. mission to collect a sample from an asteroid. According to our Goddard Institute of Space Studies, the summer of 2023 was our planet's hottest summer since global records began in 1880. June through August was a combined 0.41 degrees Fahrenheit warmer than any other summer in NASA's record. This new record comes as exceptional heat has swept across much of the world, exacerbating deadly wildfires, resulting in searing heat waves, and likely contributing to severe weather. For more details, visit nasa.gov/earth. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
The aircraft is descending over the North Base area. I have a chute. The pilot's out of the seat and the chute is good.
We had a highly competent team, very experienced, many flights under their belt. We had a number of pilots that flew the airplane. The pilot in particular that was flying that day had been on the program from the very beginning, highly experienced with the X-31.
Each mishap has its own set of circumstances and its own sequence of events. But you find similar issues: communications, complacency, assumptions that haven't been warranted, human frailties. And you have to account for these things in a program.
This is like a chain. You make a chain when you have any of these accidents, a chain of events.